Hello there, and welcome to Life Beyond Seen, where curiosity settles in like a warm blanket and science walks at a steadier pace so your thoughts can drift without rushing to keep up. Tonight, we're heading somewhere most people never picture clearly, mostly because it feels too far away to imagine. It sits beneath the oceans, far below the sunlight, below the twilight, below even the midnight depths where most deep-sea creatures drift. It's a place so removed from everyday experience that it may as well belong to another world. This quiet region is called the Hadal Zone, and while the name might sound dramatic, it's simply the scientific label for the deepest trenches of our oceans, those narrow chasms carved into the seafloor where conditions become almost unthinkably extreme. But before we drift down through those layers, and before we talk about why humanity can't truly explore that region, the way we explore mountains or deserts or even space, I'd like to know something simple. Where are you listening from tonight? And what time is it for you right now? It's always a little grounding to remember that while we talk about the deepest places on Earth, you're sitting somewhere with a glowing screen, a stable floor beneath you, and an atmosphere that isn't trying to squeeze you into a piece of paper. If you find this kind of slow exploration comforting, or if you enjoy having something gentle to fall asleep to, I'd really appreciate it if you gave the video a like, maybe even subscribed, because it helps this sleepy corner of the internet reach more people who need a quieter moment. Now let's settle in and begin, not by plunging immediately into the deepest water, but by taking a small step back to see the whole picture. Whenever people talk about the ocean, they often picture its surface first, a wide open space where ships move steadily and waves rise and fall in familiar patterns. Even as children, we learn quickly that the surface is only the start, and there's a surprising amount of water below that point. But the true scale doesn't land until you think slowly about the layers that sit beneath the surface. The uppermost part, the one we swim in, is full of light, movement, and activity. Beneath that is dimmer water, cooler, quieter. Go deeper, and the world changes again, and before long there's no sunlight left at all. You reach the region where most deep-sea documentaries take place, showing glowing creatures and drifting shapes that seem almost alien. But those scenes still aren't the deepest. They belong to depths that, while impressive, are still within the range of human-made submarines, cables, sensors and cameras. They're deep, but not impossible. The Hadal Zone is different. It begins at around 6,000 metres and extends to nearly 11,000 metres in certain trenches. To put that in a more human scale, imagine stacking more than 20 Empire State Buildings on top of each other, still beneath the water, and then lowering a fragile machine straight down to the bottom while every metre adds more weight pressing against it. At the deepest points, the pressure is more than 1,000 atmospheres, which means every square inch of any object is hit with over a ton of force. If you try to picture what that feels like, take a moment to imagine holding a single brick in your hand. It has a certain weight, firm and obvious. Now imagine a stack of bricks as tall as a building placed on top of that same hand. It sounds silly only because the human body would give out immediately. Machines built from strong metals can tolerate far more than human flesh, but even they have limits, and the Hadal Zone has a way of testing those limits in a manner that feels almost unfair. But we're not there yet. It's easier to understand why it's so challenging by following the descent more gradually. When you pass the upper layers, you reach a region that loses light quickly. Here, the temperature starts dropping, and the ocean becomes quieter, colder, and denser. The pressure increases at a rate that feels aggressive when you think about it carefully. For every 10 metres you go down, another atmosphere of pressure pushes in. At 100 metres, scuba divers already start reaching the limits of what the human body can tolerate safely. At 1,000 metres, no human body could survive at all, not even for a moment. But of course, we don't send people down that far. We send machines. Yet even machines begin to suffer. Electronics fail. Metal warps. Seals crack. Connectors jam. Materials behave differently than they do on land because the ocean's weight isn't gentle or patient. It pushes without stopping, without variation, without any regard for what we're trying to do. The Hadal zone also has a shape problem. It isn't one continuous layer of the ocean like the water above it. Instead, it's scattered around the world in isolated trenches, narrow and steep. Unlike the flat seafloor you find at mid-depths, these trenches drop suddenly like cracks in the Earth's surface. That means even accessing the edges can be difficult. You can't simply lower a platform or an elevator-like device into a stable open pit. You have to target narrow slopes, angled walls, and pockets where machines can get stuck. The terrain is unpredictable, more like a rugged mountain range turned upside down. Imagine trying to explore the inside of an impossibly deep canyon, while the atmosphere is trying to crush your equipment from all sides, and the temperature stays close to freezing. That's what scientists face every time they try to reach the Hadal zone. However, before the challenges become overwhelming, it's helpful to notice something else. Only a tiny fraction of the ocean has been explored directly, not because people lack interest, but because the resources needed to reach extreme depths are so high that only a handful of missions can be attempted each decade. And when one of those missions fails, the loss is enormous, not just in money, but in time, planning, engineering, and the morale of research teams. Many deep-sea robotic vehicles work well at moderate depths but fail instantly when pushed further. A small leak at 6,000 meters becomes a catastrophic implosion at 8,000. A minor design flaw on land becomes a mission-ending flaw below the twilight zone. The deeper you go, the less forgiving everything becomes, but that's only part of the story. Another difficulty is communication. Satellites don't reach underwater. Radio waves don't penetrate seawater well. GPS becomes useless. So once a machine is thousands of meters down, the only way to communicate is through acoustic signals, which behave more like slow-motion echoes than clear instructions. Data takes a long time to travel. Commands get distorted. In many cases, researchers have to pre-program machines and simply hope they behave correctly once they reach the depths. You can't steer them in real time. You can't make adjustments when something unexpected happens. If the machine gets stuck, there's often nothing to do but wait and hope it finds its way out or floats back up. Recovery missions aren't easy either, because even locating something on the abyssal seafloor is like trying to find a single lost key somewhere in a massive pitch-dark desert. Now imagine trying to do all of this in the trenches. The Hadal zone is the ocean's equivalent of a remote wilderness, where nothing is on your side. Not the pressure, not the terrain, not the lack of sunlight, not the cold, and not the communication delays. And yet researchers try anyway, because there's something deeply compelling about the deepest parts of the world. It's one of the last regions that remain almost entirely untouched by humans, and it contains organisms that live under physical conditions no land creature experiences. These animals aren't mythical or magical. They're simply adapted in ways that stretch the limits of biology. Their bodies avoid gas-filled spaces like lungs, because such spaces would collapse instantly under pressure. Their cells contain special molecules that prevent proteins from folding incorrectly. Their bones are often reduced or absent because rigid structures become liabilities at those depths. Their movement is slow, deliberate, efficient, shaped over millions of years by the need to survive where survival is neither expected nor easy. But even though these animals endure pressures that would destroy a submarine, they're not invincible. When scientists bring them to the surface, the pressure change kills them almost immediately, which makes direct study extremely difficult. Imagine being able to reach a new species only to find that observing it closely destroys it without meaning to. This limitation is one of the reasons why the Hadal zone remains full of unanswered questions. Each attempt to learn something risks losing the very subject of study. It creates a paradox where the deeper we try to explore, the more the environment resists our tools, our technology, and even our methods of observation. And still, people keep trying because the Hadal zone represents something more than a physical location. It's a reminder that Earth is not fully known, not fully explored, not fully catalogued or measured. Even with satellites, sensors and high-tech imaging, there remain places where human knowledge barely scratches the surface. In a time when maps feel complete and most landscapes are photographed endlessly, it's almost comforting that an entire realm of the planet refuses to be easily revealed, not out of hostility, but out of the sheer physical reality of water, pressure and depth. As we continue moving through this exploration, we'll look more closely at each reason the Hadal zone resists human presence, from pressure and engineering limits to biological challenges and the stubborn unpredictability of deep ocean geology. But for now, let's keep drifting downward in our imagination, not rushing, not forcing a conclusion, just continuing the steady descent into a part of Earth that holds more questions than answers. When people picture the ocean, the image that usually comes to mind is a calm surface with familiar colours and movements. Waves drifting in steady patterns, sunlight reflecting off the top, and maybe a few boats or gulls passing by. It feels open and reachable because it's the part we can see without effort. But if you try to follow that mental picture downward, even just a few meters below the surface, the brightness changes. It doesn't shift suddenly, it fades slowly as the depth increases. The moment light enters the water, it starts weakening because water absorbs and scatters it. That means the farther you go down, the more it slips away, until eventually there's nothing left. It's not dramatic. It doesn't happen in a single moment. Instead, the descent into darkness happens through a long stretch of diminishing colour and temperature. If you start near the surface during the day, sunlight feels normal. You can see fish, plants, and even the seafloor in shallow areas. But at 50 meters, the light becomes noticeably weaker. Shapes appear flatter and colours shift toward blue because red, orange and yellow wavelengths disappear first. Even though the ocean above you still seems bright when you look upward, everything else begins to lose definition. By 100 meters, the brightness becomes dim. You can no longer rely on the sun for visibility. It's not pitch black yet, but you can feel the difference as the surroundings take on a narrow range of colour, and the world becomes more subdued. At 200 meters, natural light continues to fade until it reaches a point where reading any kind of text or seeing fine detail without artificial illumination becomes impossible. Divers don't usually go this far without specialised equipment because the pressure and darkness create conditions the human body isn't built to handle. But machines can go farther. ROVs, submersibles and sensors continue downward without caring about sunlight. They don't need it. Still, even they record a consistent drop in visibility as the water grows darker with each passing meter. Eventually, around 1,000 meters down, the last usable traces of sunlight disappear for good. This region is what scientists call the midnight zone because sunlight never reaches it, even on the clearest days. At this point, the only light you'll see is the kind produced by organisms themselves. Bioluminescence is common in this region, because creatures here have evolved to create their own illumination for hunting, avoiding predators, attracting mates, and communicating. But even though that light exists, it's faint. It's not like flipping on a lamp. It's more like seeing a distant glow stick drifting through a vast room. Just enough brightness to give a sense of shape or motion, not enough to brighten the surroundings. As you continue descending beyond the midnight zone toward the Hadal depth range, the darkness becomes absolute. There are no shifting patterns from above, no fading rays, no colour left from the surface world. The ocean absorbs everything. A person looking out from a submersible window at those depths sees only the cone of the submersible's lights cutting into the black. Those lights reach only a small distance before the darkness swallows them. It isn't a dramatic emptiness. It's more like a consistent background with no variation, no horizon, no familiar cues. This darkness also comes with a temperature change. Water becomes colder the deeper you go until it stabilizes at just a few degrees above freezing. That cold temperature remains consistent because sunlight doesn't reach this far to warm anything. The entire environment is steady and unchanging, in a way that feels unlike anything on the surface. The cold doesn't fluctuate with seasons, weather, or time of day. It is always there, a constant factor. But the most challenging factor in this region isn't the lack of light or the low temperature, it's the pressure. While the darkness grows slowly and steadily, the pressure increases with a kind of relentless consistency. Every 10 meters adds another atmosphere of pressure. 1 atmosphere is what we feel at sea level. It's the pressure of the air on your skin right now. Humans are so used to it that we don't notice it at all. But once you go underwater, the pressure begins to build. At 20 meters, your body experiences triple the pressure you feel on land. Divers notice this because their ears, lungs, and equipment respond differently. At 100 meters, the pressure is around 11 atmospheres. Even specialized divers need training, gas mixtures, and equipment designed to handle it. At 1,000 meters, the pressure is around 100 atmospheres. Every square inch of anything at that depth experiences the equivalent of a car sitting on top of it. Machines built from metal alloys, thick composites, and pressure-resistant components start approaching their limits. The problem becomes more extreme as the depth increases. At 4,000 meters, the pressure is around 400 atmospheres. At 6,000 meters, which marks the beginning of the Hadal zone, it reaches around 600 atmospheres. And at the deepest known point on Earth, the Challenger Deep in the Mariana Trench, the pressure hits more than 1,000 atmospheres. That's more than 8 tons of pressure on every square inch. To imagine it more clearly, think about holding a bowling ball in your hand. It feels heavy but manageable. Now imagine stacking 100 bowling balls onto that same hand. Obviously, the idea is physically impossible. The human body would collapse long before that point. Even metal structures that seem strong on land can warp, crack, or implode under such force. Engineers spend years designing housings, windows, seals, and cables that can withstand these pressures. Even small imperfections, ones that wouldn't matter at all on the surface, become significant weaknesses in the deep ocean. But pressure doesn't just affect machines. It affects how fluids behave, how sound travels, and how organisms survive. Water becomes slightly denser and more stable as the pressure builds. Sound travels faster and over greater distances, which changes how communication works. Even chemical reactions inside living cells shift subtly, because molecules behave differently under such intense force. The foundations of biology adapt in ways that don't occur anywhere else on Earth. Many deep-sea creatures have developed bodies without air pockets, because internal gas cavities collapse under pressure. Fish found in the Hadal zone often lack swim bladders, the buoyancy organs that shallow water fish rely on. Instead, their bodies use specialized proteins, fats, and fluids that allow them to float or move without trapping air. Some organisms replace typical bone structures with cartilage or reduce skeletal components because rigid structures become risky. A rigid shape can fracture under pressure, whereas flexible tissue can survive better. One of the more surprising adjustments involves cell membranes. Under normal conditions at the surface, cell membranes need to remain flexible enough to function. They're made from fats and proteins that form stable, semi-fluid layers. But at Hadal pressures, those same membranes would stiffen too much unless organisms produce special molecules that act like built-in adjusters. These molecules help maintain the right amount of flexibility so that cells can operate correctly. Without those adaptations, life would fail quickly. As light fades and pressure grows, another issue emerges: navigation. Shallow water environments allow creatures to rely on visual cues, sunlight direction, temperature gradients, or features on the sea floor. But deep-sea animals must navigate without those cues. They use sound, vibrations, chemical signals, and sometimes electrical sensing. Even with these tools, distances become difficult to judge. What feels like a short movement may actually be long because there's no visual reference. Machines struggle with navigation for similar reasons. GPS signals don't penetrate water. Cameras become nearly useless without artificial light. Acoustic sensors work but provide limited resolution. A submersible trying to move across the deep sea floor has to rely on sonar, inertial navigation, or other indirect tools. This makes it difficult to locate specific sites, paths, or objects. A slight drift can cause a vehicle to miss its intended target by hundreds of meters, especially in narrow trenches. Another complication comes from currents. Even in deep water where everything seems still, there are slow-moving currents that can push vehicles off course. These currents aren't strong by surface standards, but they can interfere with delicate maneuvering. At Hadal depths, even a subtle current becomes meaningful because vehicles have limited propulsion. Most deep-sea equipment isn't designed to fight strong movement. Instead, it's designed to withstand pressure. Balancing those two needs is tough. The changes in pressure also influence any equipment that relies on electronics. Deep-sea vehicles need thick pressure housings around batteries, cameras, computers, and sensors. These housings add weight and bulk. The heavier a machine becomes, the more buoyancy it needs. But adding buoyancy materials means adding objects that must resist crushing pressure. Engineers use specialized syntactic foams, materials filled with tiny hollow glass beads that resist implosion. But even these materials can crack at extreme depths if not manufactured precisely. Cables used to lower or retrieve equipment also face challenges. They must be strong enough to handle the weight of the vehicle, but flexible enough to coil and uncoil during deployment. At the same time, they cannot collapse under pressure. A cable thick enough to survive deep pressure might be too heavy to lift effectively. A lighter cable might fail at the critical point. These kinds of design trade-offs make Hadal exploration difficult. Every choice affects another choice. Even if a machine reaches the correct depth successfully, gathering data becomes its own struggle. Cameras record only what appears within their narrow field of artificial light. Microphones pick up sounds, but sound travels so efficiently in deep water that echoes become confusing. Sampling devices must avoid contamination from other layers of the ocean. The sample taken at 10,000 meters can't simply be pulled to the surface, because pressure changes might destroy it. Engineers sometimes build pressure-preserving containers that lock in samples at depth, so their structure doesn't collapse when returning to the surface. But these containers are complex and prone to failure. As light disappears, biological activity changes too. Many Hadal creatures rely on sinking organic material from above. When animals die in shallower waters, their bodies drift downward over weeks or months, slowly decomposing as they fall. By the time they reach Hadal depths, most of the material has been consumed or broken down. The organisms that survive at the bottom must rely on sparse supplies. This scarcity forces them to use energy carefully. Slow movement, slow metabolism, and long lifespans become common strategies. They can't afford wastefulness. Every calorie matters. This environment shapes everything from the smallest microbe to the largest predator. Even bacteria behave differently under pressure. They use chemical pathways tailored to the deep ocean, producing enzymes that operate effectively at near-freezing temperatures. Some microbes survive by consuming chemicals seeping from the seafloor. Others attach themselves to sinking particles and ride them downward. All of these adaptations reveal how profoundly the deep ocean influences life. Descending through the dimming layers also reveals how quiet the deep sea becomes. Sound travels well at depth, but background noise drops significantly. There are no waves crashing, no storms rumbling, no wind pushing across the water. The only sounds are the movement of creatures, the occasional rumble of geological activity, and the distant vibrations that travel from far-off events. A submersible's engines sound surprisingly loud because the environment itself is so calm. But even then, the noise feels contained, swallowed by the surrounding water. Despite the darkness, the pressure, and the limited food supply, life does exist here. It adapts to conditions that appear unlivable. But the combination of fading light and rising pressure limits what can survive. And that limitation carries over into human exploration. Machines that work well at moderate depths fail here. Sensors that function on the surface become unreliable. Even the data we receive must be interpreted carefully because direct observation is so restricted. As one moves deeper, the environment continues to change and the challenges stack up. There isn't a single barrier that prevents easy exploration. It's the combination of many factors working together. Light fading is one problem. Pressure increasing is another. Temperature, navigation, biology, material science, and communication add more layers. By the time you reach the Hadal zone, you aren't facing one issue. You're facing all of them at once. That's why even simple tasks such as taking a measurement or retrieving a sample become complicated. Yet the limitations don't discourage exploration entirely. Instead, they set the stage for understanding the deeper reasons why the Hadal zone remains out of reach for most technology. As we continue moving through this topic, each factor contributes to the broader picture of why these depths remain so rarely visited, and why each attempt requires more planning, resources, and caution than any other environment on Earth. When most people try to picture the ocean floor, the first image that comes to mind is usually a flat sandy surface, stretching out in all directions like a calm underwater desert. That picture isn't entirely wrong for certain shallow regions, but it stops being accurate once you move into the deeper parts of the world's oceans. The deep sea isn't flat, it isn't simple, it isn't one continuous surface. Instead, it holds a landscape built from features as complex and varied as mountain ranges on land. The deeper you go, the more unusual these structures become. They aren't shaped by wind or erosion like they are on land. They're shaped by pressure, temperature, sediments, tectonic forces, and the slow movement of Earth's crust. If you could step back and see the deep ocean floor as a whole, you'd find an environment that looks more like a mismatched collection of geological surprises than a single surface. As you move past the continental shelf, the sloping region near the coast gives way to the continental slope. This slope is much steeper than people usually expect. It drops quickly, often forming canyons and ridges. Some underwater canyons rival those on land in size, carved not by rivers but by slumping sediments, underwater currents, and occasional collapses. Once you move past the slope, you reach the continental rise, where sediments build up into wide, gentle forms. This area marks the transition between the shallower parts of the ocean and the deep abyssal plains. Abyssal plains are one of the flattest surfaces on Earth, smoother in many areas than land-based deserts or salt flats. They formed as layers of fine particles settled over millions of years. At first glance, it might seem like these plains should be easy to navigate, but this is only the starting point. Even though they make up large sections of the deep sea, they're interrupted by volcanic ridges, unexpected slopes, extinct hydrothermal vents, and trenches. In some areas, the seafloor rises sharply into underwater mountains called seamounts. These mountains can reach thousands of meters high, but never break the surface. They're usually extinct volcanoes, but some are active. Their sides are steep, and currents swirl around them, carrying nutrients and sediments that shape the surrounding landscape. Moving away from seamounts, you might think the landscape becomes simpler again. It doesn't. The mid-ocean ridges extend through every ocean on Earth, forming the longest continuous mountain range on the planet. These ridges are built by tectonic activity, where magma rises to the surface and creates new crust. The spreading forces create cracks, fissures, valleys, and uplifted structures. Hydrothermal vents line parts of these ridges, releasing hot mineral-rich water that shapes chimneys and towers that look almost industrial in structure. Even though these vents are relatively small compared to the scale of the ocean, they create patches of terrain that feel distinct from everything around them. But the main focus eventually becomes the trenches. These long, narrow features mark places where one tectonic plate dives beneath another. They form shapes unlike anything else in the ocean. They're extremely steep, extremely deep, and surprisingly complex. Many people imagine a trench as a simple slit in the ocean floor, like a long straight crack. the reality is far less tidy. Trenches often curve, twist, widen, narrow, and shift direction. Some have multiple basins inside them instead of one simple bottom. There are terraces, steps, and sudden drops that occur within a few meters. Instead of one flat floor, the base of a trench might have ridges and hills shaped by sediment avalanches, shifting plates, or old landslides. In some trenches, the walls are angled sharply downward. In others, they curve inward like the sides of an uneven bowl. A single trench may contain small ridges created by compression forces. These ridges rise like miniature mountain chains, only to be surrounded on all sides by pressure and darkness. Some trenches even contain faults and cracks inside them, tiny versions of the larger plate boundaries that formed the trench in the first place. If you were somehow able to drive along the bottom of one of these trenches, the path wouldn't be smooth. It would feel like crossing a rugged, unpredictable valley with sudden shifts in texture and height. And this is only the geological part. The deep sea floor is also shaped by sediments that drift down from above. Most of this material consists of tiny particles, plankton remains, dust, debris, and minerals that slowly accumulate over centuries. But every so often, a major sediment flow rushes into a trench. These flows act like underwater avalanches, redistributing mud, silt, rocks, and organic matter in large quantities. Some flows are powerful enough to destroy equipment or bury it entirely. Because these events occur unpredictably and without warning, they create additional complexity in the Hadal landscape. Soft layers might pile up in one area, while a completely exposed rocky slope sits just a few meters away. The variety of textures is enormous. Even the chemical makeup of the deep seafloor contributes to its shape. Minerals dissolved in seawater precipitate out over time, forming crusts on rocks, or creating unusual formations. In areas near volcanic activity, minerals from hydrothermal vents accumulate and build structures that can grow several meters tall. These structures are porous and brittle, and can crumble easily under pressure or movement. As they collapse or shift, they add irregular debris to the surrounding terrain, creating slopes that aren't stable, and surfaces that break apart when disturbed. All of this means that the deep sea doesn't behave like a uniform environment. Every stretch of terrain comes with its own style of hazards. A submersible entering a deep valley might encounter uneven sediment that shifts under its weight. A robotic vehicle moving along a trench wall might slip sideways if the slope is too steep. A machine positioned over a ridge might find itself unexpectedly drifting, because currents behave differently depending on the shape of the terrain. Even small changes in seafloor shape influence how the vehicle must adjust its movements. Because this environment is so varied, exploring it requires detailed mapping. But mapping the deep sea is extremely hard. Sound-based mapping tools can provide broad outlines, but the resolution often isn't fine enough for precise navigation. The deeper you go, the harder it becomes to gather detailed information. High-resolution mapping usually requires getting close to the seafloor, but machines can't easily hover in place at extreme depths because the pressure and darkness interfere with sensors. As a result, most maps of trenches show only general shapes rather than fine details. Engineers know what the terrain looks like in broad terms, but they can't predict the small features that often make or break a deep-sea mission. The architecture of the deep sea also includes chemical gradients and temperature differences that shape where life can exist. Around hydrothermal vents, the terrain is influenced by warm water mixing with cold seawater. These mixing zones create pockets of chemically distinct areas. The boundaries between different chemical regions can shift suddenly as vents open or close. Since vents often shut down unpredictably, entire areas of the deep sea can change character within relatively short geological timespans. Structures built from mineral deposits may collapse once the vent stops supplying mineral-rich water. This adds another layer of unpredictability to the environment. Another part of the deep sea structure involves the interaction between the seafloor and the water column above it. While currents are weaker at great depths, they still flow in ways that shape sediment and transport materials. Some trenches funnel currents, concentrating their flow in certain areas. Other trenches block currents, creating isolated pockets where sediments linger. These differences create microenvironments with unique conditions. Some species thrive in one pocket but not another because of subtle variations in sediment type, oxygen level, or organic material. One of the more unusual features of deep-sea architecture is the presence of subducted materials. In trenches, as one tectonic plate moves beneath another, parts of the plate break apart. Segments may form jagged outcrops or ridges on the trench floor. These fragments can be tilted, buckled, or buried under younger sediments. They can create obstacles for machines and serve as hiding places for organisms. Some of the deepest rock samples ever retrieved from the ocean come from these areas, showing that geological activity remains active even at extreme depths. In addition to the geological variations, biological structures also influence the landscape. Tube worms near vents grow in clusters that create barriers. Colonies of microorganisms form mats over sediments. Burrows from deep-sea organisms reshape sediment patterns. Even though life is sparse compared to shallow waters, the organisms that do exist have a noticeable impact on the terrain. A patch of biological activity might stabilize sediment in one place while loosening it in another. The architecture of the deep sea also changes over time. The movement of tectonic plates constantly reshapes the sea floor. New ridges rise while old ones erode. Trenches shift slightly in direction as the plates beneath them move. Sediment layers accumulate unevenly, altering the contour of the seafloor. These changes occur slowly by human standards but steadily on geological scales. Any map drawn today might be less accurate in a century, not because the terrain changes dramatically, but because even small shifts matter when dealing with an environment where precision determines success. From an engineering standpoint, this irregularity makes building equipment incredibly difficult. Machines designed for flat, predictable terrain must instead prepare for steep slopes, uneven surfaces, sudden drop-offs, and unstable sediment. A vehicle might need to anchor itself in order to collect a sample, but the ground beneath it might not support the anchor. A sampling arm might reach for a rock only to trigger a small slide of sediment that covers the sample entirely. Equipment designed for stability at moderate depths might behave unpredictably in trenches because the terrain interrupts sonar signals. Navigation software that works well on the abyssal plains becomes unreliable in tight trench corridors. Even deploying equipment to these locations becomes challenging. To send a machine into a trench, researchers must know where the trench walls slope inward or outward. A vehicle lowered without careful planning might hit an overhanging formation. Ropes or cables risk rubbing against rock walls if the machine drifts sideways. Narrow sections of trenches limit maneuverability. The deeper a trench goes, the more its shape resembles a complex maze rather than a simple valley. While machines can reach deep waters, reaching the right location inside a trench is far more complicated than simply going straight down. The entire deep sea, with its mountains, plains, ridges, vents, canyons, and trenches, forms a physical structure unlike any environment humans normally deal with. On land, even rugged terrain is accessible with the right equipment. In space, the lack of physical obstacles means that movement is limited only by propulsion and trajectory planning. But in the deep ocean, machines must move through a landscape that combines the worst challenges of both worlds: total darkness, crushing pressure, limited navigation options, and surfaces that vary without warning. This strange architecture shapes everything that tries to enter it. It dictates where organisms can live. It determines which scientific missions succeed or fail. It explains why reaching the Hadal zone is more than simply travelling downward. It's about understanding a complex environment that refuses to simplify itself for exploration. As we continue into the next part of this journey, the terrain beneath the ocean will connect directly to the reasons the Hadal zone remains so difficult to reach. Every ridge, slope, fault, and trench adds to the challenge. and each of those elements becomes clearer as we keep moving deeper into this environment. When conversations about the deep ocean come up, it's common to hear people compare exploration of the seabed to exploration of space. This comparison usually starts with the idea that both environments are extreme and that humans struggle to operate in either one. While that general point isn't wrong, it misses the specific difficulties that make the Hadal zone far more complicated than simply building a strong enough vessel and sending it downward. The Hadal zone doesn't challenge explorers with a single obstacle. It challenges them with nearly every category of environmental limit at the same time. Each individual problem might be manageable, but together they create a barrier that only a handful of missions have ever crossed successfully. Pressure is usually the first factor people mention, and for good reason. At the deepest trenches, the pressure becomes more than 1,000 times higher than the pressure humans experience at sea level. Building a vessel that can resist that force requires materials and engineering principles that approach the limits of what current technology can handle. But pressure alone isn't the full story. Engineers can build thick pressure hulls using titanium, steel, or specialized composites. These materials resist collapse well enough when manufactured correctly, but constructing a pressure-resistant structure isn't the end of the challenge. It's only the starting point. The moment a vehicle becomes capable of resisting extreme pressure, it becomes heavier. The heavier it becomes, the more buoyancy it needs. Deep-sea vehicles rely on syntactic foam for buoyancy, which is filled with millions of tiny hollow spheres that resist being crushed. But as the depth increases, even syntactic foam must become thicker and stronger. This adds weight, which requires more foam, which adds more weight, and the cycle continues. Engineers must constantly balance strength and buoyancy so the vehicle remains functional. If it becomes too heavy, it won't rise back to the surface. If it becomes too light, it won't descend efficiently. The margin for error is extremely narrow. Designing a vessel that can withstand pressure also affects how internal systems operate. Electronics inside the pressure hull must remain dry and undistorted by pressure. Wiring, batteries, and communication devices must fit inside a limited space, which grows smaller as walls become thicker. Even minor changes in the shape or thickness of the hull influence how much equipment can be included. Engineers often have to remove instruments or reduce sampling capacity simply to make the design viable. As a result, deep-sea vehicles capable of reaching Hadal depths usually carry fewer scientific instruments compared to those used at moderate depths. Another challenge involves temperature. Even though the deep ocean stays just above freezing, the combination of extreme cold and immense pressure affects materials in unusual ways. Metals contract, seals become stiff, lubricants thicken, and electrical components behave differently. Engineers must choose materials that remain stable under these conditions, but no material is perfect. Some crack at certain temperatures, others deform after repeated exposure to high pressure. A vehicle might complete one dive successfully but fail on the second because the cumulative stress weakens a component. Communication is another serious limitation. Deep-sea vehicles can't rely on radio signals, GPS, or satellite links. Water blocks these signals almost completely. At Hadal depths, the only feasible method of communication is acoustic signalling. Acoustic messages travel slowly, often distorted by the water and the terrain. The deeper the vehicle goes, the more interference it encounters. Researchers on the surface must send instructions carefully, waiting several seconds to see whether the vehicle responds. In many cases, the delay becomes long enough that real-time control becomes impossible. As a result, vehicles must operate autonomously or follow pre-programmed routes. If something goes wrong, the operators cannot correct it immediately. Navigation becomes another complication. The Hadal zone is not an open, flat expanse. It's a collection of narrow trenches, sloping walls, irregular valleys, and unexpected ridges. Navigation systems that rely on sonar must process data in real time, but sonar only reveals part of the environment. Sometimes a vehicle receives a distorted signal and misinterprets the shape of the terrain. This can cause a submersible to drift into a slope or fail to detect a drop-off. Because the environment is so dark and sonar resolution decreases with distance, a vehicle might not detect an obstacle until it is too late. Even slight collisions at that depth can damage sensors or crack buoyancy materials. Currents contribute to the difficulty. Although deep-sea currents are slower than surface currents, they still exert force on vehicles. A slow current in the Hadal zone can push a machine off its intended path, especially in narrow trenches where the shape of the walls funnels water in complex ways. Vehicles must compensate for this movement using propulsion systems, but thrusters lose efficiency under high pressure. They also consume energy quickly and battery power is limited. Engineers must estimate how much propulsion will be needed and design the energy system accordingly. If the currents are stronger than expected, the vehicle may fail to reach its target or expend too much energy trying to stay on course. Energy management is another issue. At great depths, vehicles must carry all the energy they will use during the mission. Solar power is impossible. Tethering the vehicle to a ship with a power cable introduces the risk of snagging the cable on terrain features. Batteries must provide enough power for propulsion, lights, cameras, sensors, and sampling equipment. Using more energy for lights leaves less for propulsion. Using more for propulsion leaves less for sensors. Engineers must distribute the energy carefully to ensure the vehicle can complete the entire mission and return to the surface. Sampling presents additional problems. Collecting samples from the Hadal zone isn't as simple as grabbing a handful of sediment and bringing it up. Pressure at those depths keeps biological and chemical components stable. The moment a sample begins rising, the pressure decreases. This can destroy its structure, change its chemical composition, or kill organisms that cannot survive at surface pressure. To address this, researchers sometimes use pressure-retaining containers that lock at depth and preserve the sample's condition during recovery. But these containers are complex and prone to mechanical issues. If a seal fails, the sample becomes altered and loses its scientific value. Even the deployment of vehicles into the water brings challenges. Lowering a machine thousands of meters requires strong cables and winches. The cable must support the weight of the machine, but also its own weight. At great lengths, cables become extremely heavy. They sway with waves and wind, creating lateral forces that push the vehicle away from the desired path. Lowering equipment through rough seas increases the risk of damage before the machine even reaches depth. Weather conditions at the surface can delay missions, while underwater conditions remain unaffected by surface changes. This disconnect makes planning difficult. Another challenge arises from the difficulty of retrieving vehicles. If a machine fails to ascend, it becomes stuck on the sea floor. The only hope is that its emergency buoyancy system activates. Many deep-sea vehicles carry weights that they can release at depth. When the weights fall away, the vehicle becomes lighter and floats to the surface. But if the release system fails, the vehicle stays down. Because GPS doesn't work underwater, the exact location of the vehicle might be unknown. Searching for it becomes nearly impossible. The ocean is too large, the trench is too deep, and the terrain too complex. Lost vehicles remain on the seafloor indefinitely, unless retrieved by an extremely lucky chance. Cost becomes a significant barrier as well. Building a Hadal-capable vehicle requires specialized materials and manufacturing processes that push the limits of current technology. Very few institutions have the funding to create such machines. Even fewer can afford to operate them. A single dive can cost as much as a major scientific expedition. Insurance, maintenance, and repair costs add even more complexity. Because funding is limited, missions occur infrequently. Each mission must collect as much data as possible, but this increases pressure on researchers to minimize risk. The combination of high cost and high danger limits the number of attempts that scientists can make. The rarity of missions introduces another problem: lack of experience. Engineers and researchers learn from repeated attempts. When missions are rare, there are fewer opportunities to gather practical knowledge. Lessons from one dive may not generalize to another because each trench has its own conditions. Engineers must rely on theoretical models, simulations, and educated guesses. While these tools are valuable, they cannot replace hands-on experience. The Hadal zone remains one of the least tested environments on Earth. Biology itself creates obstacles. Organisms in the Hadal zone are adapted to extreme pressure and low energy availability. Their tissues, enzymes, and cell structures function under conditions that would damage or alter biological materials from shallower waters. Some organisms are too fragile to handle even slight pressure changes. Others break apart when exposed to currents or mechanical disturbance. This makes biological sampling difficult. Scientists must develop tools that can collect organisms without damaging them. But tools that function gently often cannot withstand the pressure. Tools that withstand the pressure often apply too much force. This contradiction is one of the biggest challenges in Hadal biology. Another major issue comes from the simple fact that the Hadal zone is far from shore. Most deep trenches are located in remote areas of the ocean, where storms, large waves, and unpredictable weather patterns are common. Operating a research ship in these regions requires extensive planning. Crew members may spend days or weeks travelling before reaching the site. Supplies must last long enough for the entire journey. Medical support must be available even though evacuation options are limited. Ships must remain stable while deploying equipment, which becomes harder in rough seas. Every logistical detail adds another layer of difficulty. Environmental conditions in the Hadal zone also change slowly over time. Sediment accumulation can alter the shape of the trench floor. Underwater earthquakes can create new slopes or trigger landslides. Hydrothermal activity can appear or disappear. Because conditions evolve, maps and previous data can become outdated. A vehicle that successfully navigated one trench 10 years ago may encounter new obstacles during a modern mission. This unpredictability forces engineers to design vehicles that can handle multiple scenarios, which increases complexity. Uncertainty extends to the chemical environment as well. The deep ocean contains gradients of salinity, dissolved gases and minerals that vary between trenches. These variations affect how equipment behaves. Some metals corrode faster in specific chemical conditions. Seals degrade at different rates. Even the density of seawater changes slightly from one location to another, which affects buoyancy calculations. Engineers must account for these variations during design, but predicting them accurately is difficult. Finally, there is the human limitation of working blind. At Hadal depths, researchers cannot observe the environment directly. They rely on images, sonar scans, and sensor readings. These sources provide useful data but lack the clarity that direct observation offers. Many scientific discoveries happen by accident during fieldwork when researchers notice something unexpected. In the Hadal zone, such opportunities are limited. Everything depends on instruments functioning correctly, following their planned route, and capturing the intended data. If anything goes wrong, the chance for discovery disappears. Taken together, these obstacles explain why the Hadal zone remains one of the most difficult places on Earth to access. It is not a single barrier that stops exploration. It is a combination of mechanical, environmental, logistical, and biological factors that multiply one another. Each attempt to explore these depths requires solving dozens of problems simultaneously. This complexity shapes every mission and influences every decision engineers and researchers make. As we continue, the focus will shift toward the intense physical forces at the bottom of these trenches and how they affect both machines and living organisms. The deeper we look, the clearer it becomes that the Hadal zone sets rules that few things can tolerate, and those rules define everything that reaches its depths. When people talk about the deep ocean, pressure usually comes up as a scientific fact that sounds impressive but distant. 1,000 atmospheres of force pressing on every square inch of a surface seems extraordinary. Yet those numbers stay abstract unless you slow down and consider what that actually means for anything that enters the Hadal zone. Pressure at those depths isn't a background detail. It is the defining force of the environment. Everything that reaches those depths, machines, organisms, rocks, and even the chemical behavior of water, operates under conditions that reshape how materials behave. Understanding this pressure is essential for understanding why so few things can survive or function at the bottom of the ocean. At the surface, the pressure we feel comes from the weight of the air above us. Even though air seems light, the column of atmosphere stretching upward is heavy enough to exert 1 atmosphere of pressure. This force is constant, and the human body is adapted to handle it without effort. But water is far denser than air, so its weight increases much faster with depth. Every 10 meters adds 1 additional atmosphere of pressure. Even recreational divers notice the difference when descending a few meters. Their ears feel the change, their equipment feels the change, and the surrounding water grows heavier. But that small change barely hints at what happens deeper down. At 100 meters, the pressure reaches around 11 atmospheres. At 300 meters, it rises to more than 30 atmospheres. As the descent continues, the numbers grow more quickly than the human mind can easily track. By the time you reach 6,000 meters, the start of the Hadal zone, the pressure has risen to around 600 atmospheres. That's 600 times the pressure at sea level, and the deepest trenches nearly double that again. The environment becomes a continuous force applying itself to every direction equally, pressing inward with no relief. This force affects everything. Even the water itself changes. Under extreme pressure, water molecules pack more tightly together than they do near the surface, altering density and the way sound moves through the environment. Sound travels faster because the molecules are closer together. This means noise from underwater earthquakes, distant ships, and even natural activity can travel long distances without weakening much. But for machines that rely on acoustic signals, this additional speed changes how the signals reflect off surfaces or scatter in the terrain. Materials behave differently as well. A thick steel sphere that would easily support heavy loads on the surface might buckle at depth. The walls of a Hadal submersible must be thick enough to resist crushing, but shaped precisely to distribute pressure evenly. Even a slight irregularity can create a weak point. Under normal conditions, a small imperfection might go unnoticed. At Hadal depths, that same imperfection can cause catastrophic failure. Engineers often examine each piece of equipment under microscopes, scanning for tiny cracks or inconsistencies that would be irrelevant in everyday use but dangerous in deep-sea missions. The process of building a pressure-resistant vehicle involves more than choosing the right material. Engineers must shape the material correctly, weld it carefully, and test it repeatedly. Many pressure-resistant vessels rely on spherical or cylindrical shapes because these distribute force evenly. Flat surfaces weaken under pressure because they create points where force focuses. Even windows must be shaped in specific ways to prevent pressure from causing fractures. Transparent materials strong enough to handle Hadal depths are extremely limited. Most crewed submersibles use very small windows, or none at all, relying instead on cameras because the engineering challenges increase dramatically with window size. Even with the best design, the vehicle still faces stress simply by existing at that depth. Pressure doesn't occur gradually in the sense that the machine settles into a resting state. It continues pressing every moment. Components compressed under pressure store potential energy. When the vehicle rises and pressure decreases, that energy releases, which can cause movement or deformation. Engineers must design equipment to withstand not only the intense compression at depth, but also the expansion that occurs during ascent. Repeated dives stress materials in different ways, and over time, even the strongest equipment may weaken. Living organisms face these pressures differently. Instead of resisting the environment with rigid structures, they adapt their bodies to function within it. Many deep-sea creatures avoid gas-filled organs entirely. Fish in shallow waters often rely on swim bladders to control buoyancy, but such organs would collapse instantly in the Hadal zone. Creatures that live at these depths typically lack rigid air pockets. Their bodies store buoyancy through fats, specialized molecules, and careful balancing of internal fluids. Their tissues adjust to pressure naturally because everything inside them remains at equilibrium with the external environment. Cells must also adapt. The fluid inside a cell behaves differently at extreme pressure. Proteins, the molecules responsible for nearly every cellular task, risk folding incorrectly. When this happens, the proteins lose their function, and the organism cannot survive. To compensate, Hadal organisms produce stabilizing molecules that prevent protein deformation. These molecules help maintain normal biological processes even under compression. Without them, critical processes such as metabolism and cell division would break down. The membranes surrounding cells also require adaptation. A membrane must remain flexible enough for nutrients and signals to pass through, but strong enough to maintain its structure. Under high pressure, membranes tend to become more rigid. Hadal organisms counter this by adjusting the composition of their membranes, adding molecules that keep them at the proper consistency. These adjustments allow the organisms to function at pressures that would kill most life on the surface. Despite these adaptations, life at Hadal depths operates at a slower pace. The pressure influences chemical reactions, often slowing them down. Lower temperatures also contribute. Many deep-sea processes occur gradually because the conditions don't support fast or energy-intensive activity. This affects how organisms grow, move, and interact with their environment. Predators in these depths don't chase prey with speed. They rely on careful, efficient movement. Prey species often move slowly because energy conservation becomes essential. The crushing weight of the environment influences everything from behavior to lifespan. Pressure also affects the chemistry of the seafloor. In some cases, it stabilizes minerals that would break down at shallower depths. In other cases, it forces molecules into arrangements that don't occur on land. Certain chemical reactions only happen under high pressure, making the Hadal zone a unique laboratory for understanding Earth's geology and biochemistry. The shape of the trenches, the movement of tectonic plates, and the behavior of sediments are all influenced by the immense force pressing down from above. Even rock structures deep below the sediment layers experience stress from the weight of the water column. Machines that attempt to operate in this environment must account for every aspect of this pressure. Seals, bolts, joints, gears, and even adhesives behave differently. Lubricants thicken, making moving parts slow or unresponsive. Electronics generate heat, but heat disperses differently at those depths. If a circuit overheats, repairing it becomes impossible until the vehicle returns to the surface. Engineers must design systems that function reliably despite these unusual constraints. One of the most dramatic effects of pressure is the potential for implosion. Unlike an explosion, which sends fragments outward, an implosion occurs when external pressure collapses an object inward. If a part of a submersible fails, the pressure forces the surrounding water into the space faster than the human eye can track. The collapse happens in a fraction of a second. This danger means that every component must be tested far beyond the pressures expected during the mission. Even then, unexpected failures can occur because the pressure reveals weaknesses that surface tests never detect. Pressure also affects sound in practical ways. While it allows sound to travel farther, it also alters how sound waves reflect off surfaces. A sonar pulse sent into a trench might bounce off multiple surfaces before returning, creating echoes that complicate the interpretation of the data. Operators must evaluate these signals carefully to avoid misreading the terrain. A misinterpretation could cause a vehicle to descend into an unexpected slope or collide with a ridge. Because visibility is minimal, sonar becomes the main method of seeing the environment, and pressure affects its accuracy. The silence of the Hadal zone creates its own challenges. With little biological activity and few disturbances, the environment remains quiet except for occasional geological sounds. For engineers, this means that noise from the vehicle itself becomes a major factor in navigation. Thrusters, pumps, and mechanical movements create sound that can interfere with acoustic communication and sonar readings. Engineers must design vehicles that operate quietly, but quiet operation is difficult to achieve while resisting extreme pressure. This silence also affects biological studies. Many deep-sea organisms rely on sound for communication or sensing. When a vehicle enters the environment, the noise it produces may disturb them or alter their behaviour. This complicates research because it becomes difficult to observe natural patterns when the presence of a machine changes how organisms behave. Researchers must develop techniques that minimize disturbance, but pressure-resistant vehicles often produce unavoidable noise. Pressure influences even the simple act of shining a light. At depth, water absorbs light differently. Strong lights fade quickly, and the intense illumination can startle deep-sea creatures. Cameras must adjust to the limited visibility. Engineers use high-sensitivity sensors that can gather information from small amounts of light. These sensors allow researchers to see farther than expected, but the environment still absorbs most illumination quickly, limiting the observable range. Another factor is the pressure-induced behavior of sediments. Sediments compact under pressure, becoming denser than those found in shallower waters. A vehicle landing on the seafloor risks sinking into soft material. Engineers must design landing gear that distributes weight evenly to prevent the vehicle from getting stuck. But the nature of the sediment can vary dramatically within short distances. One section may be firm while another is loose. This unpredictability requires caution when approaching the seafloor. Pressure also shapes the movement of water. Although deep-sea currents are usually slow, they behave differently at extreme depths. The pressure compresses water slightly, changing its density. When combined with temperature variations, this creates layers of water that behave independently. Vehicles passing through these layers may experience sudden changes in buoyancy. An unanticipated shift could cause a vehicle to ascend or descend unexpectedly. Engineers must design systems that can adjust automatically to maintain stability. Even the process of descending through the water column involves pressure management. As a vehicle sinks, pressure increases quickly. The structure must withstand this change without deforming. Engineers often test vehicles in pressure chambers before sending them into the ocean. These chambers simulate the pressure at depth, allowing researchers to identify weak points. But pressure chambers cannot replicate every condition perfectly. Real ocean pressure behaves differently than controlled simulations because the environment involves temperature changes, water chemistry, and dynamic forces. Life at depth demonstrates how powerful adaptation becomes when organisms must function under such extreme forces. Some species use pressure to their advantage. Certain chemical processes become more efficient under pressure. Some organisms rely on pressure to maintain their structural integrity. Without the crushing weight above them, their bodies might expand or deform. This illustrates how deeply integrated pressure becomes in biological systems. It is not simply tolerated, it becomes part of the organism's basic functioning. Pressure also affects the survival of microbes. These microorganisms have unique biochemical pathways that operate under extreme compression. Their proteins are shaped specifically for these conditions. When brought to the surface, these microbes often die quickly because the pressure changes disrupt their internal chemistry. Studying them requires special equipment that maintains their habitat conditions throughout the journey. All of these factors contribute to the overall difficulty of exploring the Hadal zone. Pressure isn't the only challenge, but it influences every other challenge. It affects navigation, sampling, design, communication, and biology. It shapes the landscape and alters how machines behave. It dictates the strategies researchers must use. No matter what part of the mission you examine, pressure remains a central force. As we continue into the next section, the focus gradually shifts from pressure itself to how life in these depths adapts to the combination of darkness, temperature, and physical constraints. The environment doesn't simply challenge machines, it shapes every living organism that survives within it, creating forms of life that operate under conditions unfamiliar to anything found closer to the surface. Darkness in the Hadal zone is not an occasional condition or a temporary absence of light. it is permanent. Sunlight never reaches these depths, not even as a faint glow or a distant shimmer. Every wavelength is absorbed higher in the water column, long before it can come close to the trenches. Because of this, the Hadal zone exists in absolute darkness, a type of darkness that remains the same regardless of time, weather, or season. This constant absence of light shapes every organism, every behaviour, and every method of survival in the environment. Most life on Earth relies on light in some form, either directly or indirectly. Plants need it for photosynthesis. Animals rely on it for visual cues, navigation, hunting, and communication. Even in shallow waters, the behaviour of organisms shifts throughout the day as sunlight changes angle and brightness. But none of these cues exist in the Hadal zone. Life here adapts to a world where vision is limited or non-existent, and many of the strategies that help organisms survive close to the surface become irrelevant. To understand how darkness reshapes life in the Hadal zone, it helps to look at the transition through the water column. As depth increases, sunlight gradually fades. Organisms at moderate depths begin to rely more on senses other than sight. Bioluminescence appears in the midwater as a tool for communication or attraction, but by the time you reach 1,000 meters, sunlight is gone completely. Beyond that point, every organism exists in an environment where the only visible light comes from the organisms themselves, or from human intrusion through deep-sea vehicles. In shallower waters, visual systems are precise and varied. Eyes adjust to light levels, detect colour, perceive movement, and help animals track their surroundings. In contrast, eyes in Hadal species often become greatly reduced or absent. Maintaining complex visual organs takes energy, and in an environment with no light, that energy provides no benefit. Natural selection tends to favour traits that support survival, and in this case, the absence of light makes vision unnecessary. As a result, many Hadal creatures either lose their eyes entirely or retain simple light-detecting structures that have limited function. Some organisms retain eyes, but modify them to pick up faint glows. These glows can come from bioluminescent organisms drifting nearby, or from chemicals reacting in slow decay processes. The eyes aren't looking for shapes or movement in the way surface creatures do. Instead, they focus on minimal changes in the environment that might indicate food, danger, or the presence of other organisms. In many cases, these eyes are oversized relative to the organism's body, not for sharp vision, but for maximizing sensitivity to any available light at all. The absence of sunlight also affects coloration. Many Hadal creatures appear pale, translucent, or uniformly dark when viewed under artificial light. Because no natural light reaches them, coloration serves little purpose. Bright colours, complex patterns, and camouflage methods based on visible cues offer no advantage. Instead, biological materials that make up skin, scales, or shells reflect their natural chemical composition without additional pigments. This often results in animals that appear plain when compared to their shallow water counterparts. While vision loses importance, other senses become more valuable. Sound travels efficiently in deep water, and many organisms adapt to detect vibrations rather than light. Sensory structures along their bodies pick up pressure waves from movement nearby. These cues help them identify potential prey or predators without relying on vision. Chemical signals also become important tools for navigation and communication. Some Hadal organisms track faint chemical trails left by decaying matter or other animals. Even minute differences in chemical concentration can guide them toward food sources in an environment where meals are infrequent. Darkness also influences behaviour patterns. In shallow waters, daily cycles of sunrise and sunset shape feeding, migration, and reproduction. In the Hadal zone, there is no day-night cycle. Conditions remain constant throughout the year. Organisms develop behaviours independent of any external rhythm. Their activity patterns drift based on internal rhythms, food availability, or environmental cues like temperature shifts or water movement caused by deeper currents. Without external cues, These behaviours become adaptable and slow-paced, designed for conserving energy. Because food is scarce, Hadal organisms adopt strategies that minimise energy use. Movement tends to be slow and deliberate. Many species wait for food to drift toward them, rather than actively searching for it. Predators often rely on ambush strategies, reacting only when prey comes close enough to detect through vibrations or chemical signals. Darkness forces organisms to rely on efficiency, and every movement becomes a calculated action. Some organisms produce their own light through bioluminescence, although this is less common in the Hadal zone than in midwater regions. Bioluminescence in the Hadal zone tends to be functional rather than decorative. It may help lure prey, deter predators, or signal to members of the same species. The mechanisms vary. Some animals store chemical compounds in their tissues that produce light when mixed. Others rely on symbiotic bacteria that emit light as a natural byproduct of their metabolism. This light, however, is not bright enough to illuminate the environment. It serves narrow, specific purposes and usually appears as brief flashes or small points. Darkness also affects the structure of ecosystems. Without light, photosynthesis cannot occur. This means that all energy entering the Hadal zone comes from above, either as organic particles drifting down from surface waters or as occasional larger food falls like dead fish or marine mammals. The lack of sunlight forces Hadal food webs to rely on resources that arrive unpredictably and slowly. Microbes break down organic material, forming the base of the food chain. Larger organisms feed on these microbes or on particles suspended in the water. Predators feed on smaller organisms that have adapted to the low-energy environment. The darkness shapes biological strategies at every level. Microbes use enzymes that function effectively under low-energy conditions. They process chemicals found in sediments, sometimes relying on reactions that only occur under high pressure. These microbes form large mats or colonies that grow slowly but consistently. Larger organisms graze on these mats, moving from one patch to another in search of new feeding grounds. Some Hadal species rely on scavenging. When a dead organism from higher in the water column sinks to the Hadal zone, it becomes a rare feast. Scavengers gather quickly, using chemical cues to locate the food source. Their feeding strategies must be efficient because the opportunity may not come again for months or years. The darkness ensures that food cues travel farther through chemical diffusion, helping scavengers locate food without relying on visual signals. The darkness also influences reproduction. Many species rely on chemical signals rather than visual displays to attract mates. Some release clouds of gametes into the water, allowing fertilization to occur through chance encounters. Others use low-energy strategies that require minimal movement. Carrying eggs or young can be challenging due to the limited availability of food. So many species develop methods that minimize the need for parental care. Darkness even affects how organisms develop structurally. In a world without light, there is no need for pigments that protect against UV radiation. There is no need for visual markings that warn predators or attract mates. Many organisms allocate resources differently. Instead of spending energy on colour or vision, they invest in pressure-resistant tissues, sensory structures for detecting chemical signals, or metabolic systems that operate efficiently at low temperatures. The physiology of Hadal organisms shows subtle but important changes compared to shallow water species. Their muscles often contain lower densities of fast-twitch fibres because they rarely need strong bursts of movement. Their bones, if present, contain materials that remain stable under pressure. Many have flexible bodies that compress slightly under pressure, adapting to the environment rather than resisting it. This flexibility allows them to maintain internal equilibrium. Pressure and darkness together influence brain structure. Because visual processing requires significant energy, organisms in the Hadal zone often have reduced visual centers. Instead, their brains allocate more resources to processing chemical and mechanical cues. This redistribution of function allows them to survive despite the limited availability of food. Darkness also contributes to the structure of the seafloor community. Sediments accumulate gradually from material falling from shallower waters. In the absence of light, plant life does not grow to bind the sediments. Instead, microbial communities stabilize the surface. Their slow, steady activity creates a thin layer of biological material that shapes the distribution of nutrients. Larger organisms burrow through these layers, redistributing sediments and altering the availability of resources. This cycle continues constantly, reshaping the seafloor through simple, repetitive processes. Deep-sea currents introduce another variable. Even though currents are slow, they carry suspended particles across the seafloor. Organisms adapt to the consistency of these flows, positioning themselves to capture particles or using their bodies to sense slight changes in water movement. In darkness, these cues become essential for locating areas with higher food concentration. The absence of light also affects how predators and prey interact. Without visual stealth or camouflage, many predators rely on sudden bursts of movement triggered by mechanical cues. When prey move through the water, the vibrations alert predators. Prey species must remain still or move slowly to avoid detection. This leads to behavior patterns that focus on minimizing disturbances. Some species flatten their bodies against the sediment to reduce pressure waves. Others curl into compact shapes to protect vulnerable parts. Darkness even shapes competition. Resources are scarce, and organisms must share limited food supplies. Instead of aggressive territorial behavior, many species adopt strategies that reduce direct competition. They spread out across the seafloor or occupy slightly different ecological niches. Some focus on suspended particles, while others feed directly on sediment. This partitioning of resources reduces conflict and allows multiple species to coexist. The long-term impact of darkness extends to the evolutionary history of the species that inhabit the Hadal zone. Over millions of years, these organisms diverge from their shallow water relatives. They develop unique adaptations that would be disadvantageous at the surface, but essential at depth. Some species become so specialized that they cannot survive even slight changes in pressure or temperature. Research on Hadal organisms reveals variations in genetic material that relate specifically to pressure and darkness. Genes responsible for structural proteins, membranes, and metabolic pathways show modifications that allow them to function under extreme conditions. These adaptations demonstrate how life shifts in response to the absence of light, reshaping fundamental processes. Studying these adaptations poses challenges. When organisms are brought to the surface, the absence of pressure and the introduction of light can cause rapid changes in their bodies. Tissues that function at depth may collapse or deform. Chemical reactions may shift. Even the presence of artificial light can influence their behavior. Researchers must develop specialized methods to examine them without altering their natural state. Darkness also affects how scientists observe the Hadal zone. Without light, visual data depends entirely on artificial illumination. But strong artificial lights can disturb organisms or create misleading impressions. What looks like a plain surface under lights may appear different under natural conditions. Cameras must be sensitive enough to record faint movements and low-light activity without disrupting the environment. In addition, darkness limits how far vehicles can see. Even the strongest lights penetrate only a short distance. Sonar becomes essential, but sonar cannot capture the detailed behavior of organisms. As a result, researchers often work with sparse or incomplete data. This makes it difficult to build a full picture of how Hadal ecosystems operate. Despite these obstacles, each study contributes to understanding how darkness reshapes life at depth. The absence of light simplifies some aspects of biology while complicating others. Vision fades, but other senses strengthen. Color disappears, but chemical and mechanical cues gain importance. Movement slows, but efficiency improves. Every adaptation reflects the same basic truth. In the Hadal zone, survival depends on functioning in a world where light offers no guidance. As we continue onward, the focus will shift toward the limitations of technology and how human-made systems struggle to match the biological adaptations that natural organisms develop over millennia. The constraints of darkness and pressure influence machines just as they influence life, and the next section moves toward understanding those technological limits more fully. When people imagine sending machines into the deepest parts of the ocean, the idea often seems straightforward. Build something strong enough, attach the right sensors, and lower it into the water until it reaches the target depth. That picture feels simple, because most machines we use in daily life follow predictable rules. If you need a stronger bridge, you use stronger materials. If you want a more durable phone, you use tougher glass. But the Hadal zone doesn't follow the same scale. The environment forces machines to deal with pressures and temperatures far outside what most materials are designed for, and these conditions create limitations that aren't always obvious. The first limitation involves material strength. Every engineering material used in deep-sea vehicles, from metals to composites, has a breaking point. At the surface, that breaking point might appear extremely high. Metals like titanium or hardened steel can support loads far beyond what human structures usually require. But when you place these materials under thousands of atmospheres of pressure, their behavior changes. They compress, deform, and respond to force differently than they do in air. Engineers must understand not only how materials behave under static load, but also how they respond to long-term stress, repeated dives, temperature fluctuations, and contact with seawater. Water produces corrosion, which complicates material selection further. Salt water corrodes many metals quickly. Even corrosion-resistant metals eventually degrade. Titanium alloys resist corrosion well but are expensive and difficult to machine. Stainless steel, often used in engineering applications, corrodes slowly over time. Specialized coatings can help, but coatings can crack under pressure or temperature changes, exposing the underlying metal. A vehicle may survive one dive without visible damage, but small cracks might form that become weaknesses during the next descent. Syntactic foam, the buoyant material used to keep deep-sea vehicles afloat, has its own limitations. Syntactic foam consists of resin filled with hollow glass beads. Each bead must withstand immense pressure without collapsing. At moderate depths, these foams perform well, but the Hadal zone pushes them near their limits. If even a small fraction of the beads collapse, the foam loses buoyancy. That change might be negligible on the surface, but at depth it can affect stability. Engineers must calculate how much foam is needed to balance the weight of the pressure hull, batteries, sensors, and other equipment. If the foam fails, the vehicle risks sinking uncontrollably. Another limitation comes from the thickness of the pressure hull. To withstand the immense force, the hull must be thick and strong, but thicker hulls reduce interior space. This affects how many sensors, batteries, and samples the vehicle can carry. Engineers often face trade-offs. They might want to include high-quality cameras, powerful lights, advanced sampling equipment, and a large battery pack. But the hull may not have enough space for everything. Even if it does, adding more equipment increases weight, requiring more buoyant material. That buoyant material takes up space and can alter the vehicle's shape or hydrodynamics. Shape matters because the deeper the vehicle travels, the more important it becomes to avoid design features that focus pressure unevenly. Flat surfaces create weak points. Sharp corners concentrate force. Large openings or viewports require reinforcement. The safest shapes are smooth and rounded, which distribute pressure evenly. But these shapes don't always align with practical engineering needs. For example, a perfectly spherical vehicle is ideal for resisting pressure, but it is not ideal for carrying large robotic arms or specialized sampling tools. The challenge becomes designing a structure that maintains strength while still allowing complex functionality. Windows present a major issue as well. Transparent materials strong enough to endure Hadal pressure are limited. Many submersibles use acrylic or quartz windows, but window size must remain small. The larger the window, the more pressure it experiences, Even small windows require significant thickness. As a result, human-operated submersibles often rely on cameras rather than direct viewing. Cameras themselves must be enclosed in pressure-resistant housings, which reduce image quality. Engineers must choose between better visibility and better safety, with safety always taking priority. Electronics behave differently under these conditions, and pressure-resistant housings only solve part of the problem. Batteries lose efficiency in cold temperatures. Some battery chemistries become unstable when exposed to extreme pressure. Large pressure housings reduce the amount of space for batteries, meaning vehicles must operate with limited power. Running lights, cameras, thrusters, and sensors consumes energy quickly. Engineers must plan missions carefully, balancing how long the vehicle can stay at depth against its available power. If power runs low, the vehicle must release ballast and ascend, even if it has not completed its objectives. Thrusters themselves require specialized design. Standard electric motors depend on lubricants that change viscosity in cold conditions. Bearings can seize. Motors can draw more power than expected. Thrusters must be enclosed in housings that protect them from pressure but allow water flow. Creating a seal that maintains integrity at Hadal depths while allowing rotating components to move freely is technically demanding. Any failure in the thruster system risks the vehicle's ability to navigate or maintain position. Cables and connectors also create vulnerabilities. While it might seem simple to run wires between systems inside the vehicle, each connection must withstand pressure. Tiny imperfections in a connector can cause leaks. A leak the size of a pinhole can disable electronics or cause short circuits. Engineers use specialized underwater connectors, but even these can fail if not assembled carefully. Many parts must be purchased at high cost or built custom, adding complexity to the engineering process. Another problem involves the limits of robotic manipulation. Collecting samples at depth requires robotic arms, claws, or scoops, but mechanical arms must resist pressure and remain functional in cold temperatures. Hydraulic systems compress under pressure, altering performance. Electric motors become sluggish. The joints in robotic arms require seals that maintain movement while preventing water intrusion. Sediment can clog joints. Strong currents can push the arm off target. Even small adjustments become difficult, and sample collection can take far longer than expected. Because sensors must operate in darkness, vehicles rely on powerful lights. But lights generate heat, and heat dissipates poorly in cold water. Engineers must balance illumination with thermal management. If lights overheat, they shut down or break. If they remain too dim, the cameras cannot collect useful data. Cameras also suffer from limitations. Image resolution decreases when housed behind thick pressure-resistant glass. Condensation can form inside housings if humidity control fails. Focus mechanisms may not work reliably under pressure. Sonar becomes essential for navigation and mapping, but sonar systems also have limits. High-frequency sonar offers better resolution but does not travel far. Low-frequency sonar travels farther but provides less detail. The walls of trenches create complex echoes. A sonar pulse might bounce off multiple surfaces before returning, making it difficult to interpret the data. Engineers must develop algorithms that filter out noise and identify the correct reflections. But these algorithms cannot anticipate every possible formation or obstacle. Navigation without GPS adds even more difficulty. Vehicles must use inertial navigation systems, which track movement based on internal sensors. But small errors accumulate over time, causing drift. A vehicle might believe it is moving in a straight line when it has actually veered off course. Acoustic transponders placed on the seafloor can help, but placing them requires additional missions. The lack of reliable navigation systems limits the vehicle's ability to return to specific points or follow precise paths. Another limitation arises from how vehicles are deployed. Lowering a vehicle into the ocean requires a strong cable and a winch system. At great depths, the cable's weight becomes significant. The cable must support not only the vehicle but also its own length. For Hadal missions, tethered vehicles are often impractical because the cable becomes too heavy, or risks entanglement in trench walls. This forces engineers to rely on autonomous or free-falling vehicles, which have less control. Freefall vehicles drop to the seafloor using gravity and ascend by releasing ballast weights. This method works well for some missions, but the lack of control during descent means the vehicle cannot avoid obstacles. If it lands on an unstable slope or near a rock formation, it may tip over or become stuck. Engineers must choose descent paths carefully, but mapping data often lacks detail. This uncertainty creates risk every time a vehicle enters a trench. Autonomous underwater vehicles, AUVs, offer more control, but they require sophisticated programming. They must avoid obstacles, navigate low visibility environments, monitor their power usage, and follow complex mission plans. Each of these tasks becomes harder under pressure. If an AUV detects a problem, it must make decisions independently, and mistakes can be costly. A single wrong turn could lead it into a terrain feature that damages the hull or traps the vehicle. Communication limitations reduce the ability to intervene. Acoustic communication provides only small amounts of data at slow speeds. Engineers cannot stream video in real time. They cannot pilot the vehicle directly. They must rely on status reports sent at intervals. If a problem arises, the vehicle must resolve it on its own, or return to the surface prematurely. The limitations of communication restrict the complexity of tasks that AUVs can perform. Cost adds another layer of limitation. Building a Hadal-capable vehicle requires specialized materials, custom manufacturing, and rigorous testing. Few research institutions have the resources to invest in such equipment. Maintaining these vehicles also costs money. Each dive risks damage, and repairs often require replacing expensive components. Because missions are rare, each one carries pressure to succeed. This limits experimentation and reduces opportunities for iterative improvement. Testing equipment before deployment can help, but simulations cannot replicate every condition. Pressure chambers test hulls, but they may not reproduce the long-term effects of cold seawater. Mechanical systems may behave differently underwater than in a controlled environment. Engineers must anticipate failures that they have never seen before. Even small oversights can result in major problems at depth. Human-operated submersibles face additional restrictions. While they offer the advantage of direct observation, they require even more robust construction. Life support systems must operate flawlessly. Windows must withstand pressure. The vessel must maintain a stable internal environment despite external conditions. These requirements make crewed vehicles more complex and expensive to build. As a result, very few crewed submersibles can reach Hadal depths, and their dives remain rare. Every part of Hadal engineering involves trade-offs. A vehicle designed to maximize strength might sacrifice maneuverability. One built to carry large samples might sacrifice endurance. One optimized for mapping might carry fewer scientific instruments. Engineers must decide what matters most for each mission, knowing that no single vehicle can address every challenge. Even when a vehicle succeeds in reaching the bottom and returning safely, the limitations of materials show up afterward. Pressure cycles can fatigue metals. Seals may require replacement. Electronics may need recalibration. The vehicle might need months of maintenance before its next dive. This reduces the number of missions it can complete in a given year. These limitations do not make exploration impossible, but they slow it down and restrict what can be achieved. For every technological improvement, new challenges emerge. The Hadal zone pushes machines to their limits in ways that no other environment does. Unlike space, where the primary challenge is the absence of pressure, the deep ocean challenges machines with both presence and magnitude of pressure, combined with darkness, cold, unpredictable terrain, and limited communication. As we continue from here, the attention will turn toward what happens when these technological boundaries meet the organisms that call the trenches home. The next section moves further into understanding how deep-sea creatures evolve under conditions that machines struggle to survive, highlighting contrasts that reveal how life adapts when technology reaches its limits. When machines finally reach the Hadal zone after all the planning, testing and adjustments made to prepare them, they encounter conditions that push every system to operate at the edge of its capabilities. Reaching the deepest parts of the ocean is not only about surviving the descent but also functioning once the vehicle arrives. Machines do not simply enter a calm, empty world. They meet an environment defined by pressure, darkness, cold, shifting terrain, chemical variations, and biological activity that behaves differently than anything on the surface. The moment a machine crosses into the Hadal environment, the interaction between technology and natural conditions becomes a constant negotiation. During the descent, temperature drops steadily until it settles around a few degrees above freezing. Electronics must handle this cooling process without failing. Some systems become less efficient, and others may not behave as expected. Thrusters that worked perfectly during testing near the surface may respond sluggishly. Batteries drain differently at low temperatures. Because power management is essential for a successful dive, this temperature shift immediately affects mission planning. Engineers often have to compensate for these conditions by overestimating the amount of energy required, which shortens the amount of time the vehicle can spend at depth. Pressure increases rapidly as the vehicle sinks. Even though the hull is designed to withstand this force, sensors, cables and joints react to compression. In some cases, plastic components become brittle. Metals contract slightly. Connectors tighten or loosen unexpectedly. Engineers who design these systems understand the physics, but the real ocean environment still provides surprises. A component rated for a certain pressure might behave differently after prolonged exposure. Each dive becomes another data point for understanding how technology performs in the Hadal zone. As the vehicle gets close to the bottom, sonar becomes increasingly important. Sonar pulses help the machine build a map of its surroundings, but reflections behave differently near steep trench walls. The walls can deflect signals away or create multiple overlapping echoes. This forces the navigation software to interpret incomplete information. The machine must adjust its position carefully, especially if the mission requires working near the seafloor. Because visibility is limited, even small errors in sonar interpretation can lead to unintended collisions. When the machine finally lands, it often meets a surface that is not uniform. The seafloor may contain soft sediments that shift under weight, or hard plates that cause the vehicle to tilt. Landing gear spreads the load across a larger area, but the lack of detailed mapping means the vehicle cannot always predict the best landing spot. A slight shift in the sediment might destabilize the vehicle. Engineers must plan for these scenarios and give the machine systems that help it recover balance. But recovery systems add weight, and weight requires more buoyancy, which affects the design in other ways. Once on the seafloor, cameras activate. They rely on artificial lights, because no sunlight exists below several thousand meters. But artificial light changes the environment. It reveals organisms that normally stay hidden. Some creatures move away from the light, while others remain still or behave in unusual ways. The machine becomes both an observer and a disturbance. Light can reflect off particles in the water, creating visual noise. Cameras must adjust for this. Sensors must compensate. Engineers must interpret images knowing they may not reflect natural behavior. Lighting systems also interact with the environment in other ways. Lights generate heat, and at great depths, heat disperses slowly. This means the machine must manage temperature carefully. Excess heat might affect nearby sensors, or cause condensation inside housings. Lights that grow too warm can fail, leaving the machine without visibility. Engineers must design systems that balance illumination with thermal stability. This often limits how long lights can remain at maximum brightness. Biological interactions become important as well. Some Hadal organisms show curiosity toward machines. Small scavengers may approach sensors or lights. Larger organisms may bump into components or become entangled in external structures. While these encounters rarely damage the vehicle, they can interfere with data collection. When organisms settle on lights or cameras, visibility decreases. Some vehicles include protective covers or cleaning mechanisms, but these add complexity and potential failure points. Sampling equipment faces its own difficulties. Sediments at Hadal depths can range from soft mud to dense clay. A sample scoop might penetrate too deeply in soft sediments, causing the machine to sink slightly. In harder sediments, the scoop may not penetrate at all. Robotic arms must adjust grip and pressure carefully. Too much force risks damaging delicate organisms or breaking the tool itself. Too little force leaves the sample incomplete. Engineers must program robotic arms to operate with precise movements, despite the challenges created by pressure and temperature. Collecting biological samples becomes even more difficult. Many Hadal organisms are fragile. Their bodies may collapse or deform when handled. Pressure-retaining containers help preserve samples, but these containers must seal perfectly at depth. A tiny flaw in a seal or a small misalignment prevents the container from holding pressure, rendering the sample unusable. Engineers must design containers that lock automatically under high pressure and remain secure during ascent. Chemical sampling encounters similar issues. Water chemistry at Hadal depths differs from shallower regions. Dissolved gases, minerals, and organic compounds behave differently under pressure. When water samples rise, pressure decreases and chemical equilibria shift. Some compounds precipitate out of solution. Others react with oxygen introduced during ascent. To obtain accurate data, engineers must design systems that isolate water samples quickly and preserve them under pressure. These systems involve numerous small valves and chambers, each of which must function perfectly under extreme conditions. One of the biggest challenges arises when the machine begins to move across the seafloor. Even slight movements can disturb sediment. The thrusters that move the vehicle stir up particles that reduce visibility. This creates a feedback loop where the machine must slow down or stop until the sediment settles. Engineers try to reduce this effect by positioning thrusters at angles that minimize disturbance, but no design eliminates the issue entirely. The environment responds to every action the machine takes. Currents near the seafloor can shift unexpectedly. While deep-sea currents are slow, they concentrate in narrow trench corridors. A machine might encounter a sudden push that alters its path. Thrusters must counter these movements, but thrusters consume battery power quickly. When the machine has limited power reserves, every correction reduces the mission's duration. Engineers must balance accuracy and endurance, knowing that unexpected currents may shorten the dive. Acoustic communication becomes more complicated at the bottom. The seafloor, trench walls, and various geological features scatter sound waves. Messages sent from the surface may take longer to reach the machine. Signals from the machine may echo or distort. To compensate, communication software must filter and interpret signals carefully. But filtering consumes processing power, and processing power consumes energy. Engineers must optimize these systems so they remain functional without draining the battery. Navigation challenges continue to appear. Even with sonar, vehicles often struggle to identify slopes or ridges until they are nearby. Cameras help, but only within limited range. If the machine must follow a predetermined path, any deviation creates problems. If the task requires fine maneuvering, such as collecting samples or deploying instruments, the machine must make continuous adjustments. Each adjustment carries a risk of misinterpreting sensor data. Technology also interacts with geological features in ways that complicate missions. Hydrothermal vents, while less common at Hadal depth than at mid-ocean ridges, still appear in some trenches. These vents release hot water rich in minerals. When this water contacts colder seawater, minerals precipitate out, creating plumes that interfere with sensors. A machine passing through such a plume might experience temperature fluctuations or clogging of filters. Engineers must design vehicles that can avoid or withstand these conditions. Seafloor instability presents another challenge. Sediment layers can shift. Rocks may fall from trench walls. A vehicle working near a steep slope risks encountering small landslides or sediment flows. Even minor slides can bury sensors or cover parts of the vehicle. Engineers must anticipate these risks and include emergency ascent mechanisms. These mechanisms usually involve dropping ballast weights, but they must be designed to function reliably, even if parts of the vehicle are buried or damaged. As the mission progresses, the machine continues interacting with the environment. Biological noise, geological noise, and artificial noise from the machine itself influence sensor performance. Temperature variations affect battery efficiency. Pressure changes influence material behavior. Every moment at depth adds cumulative stress to the vehicle. Engineers design vehicles to withstand these stresses, but repeated dives eventually weaken components. The Hadal zone test every piece of technology continuously. When the time comes to ascend, new challenges appear. As the vehicle rises, pressure decreases. This causes the hull and other components to expand slightly. Seals must maintain integrity despite this expansion. Electronic housings must remain dry. Buoyancy changes may alter the machine's stability. If the ascent process is not controlled carefully, the vehicle may rise too quickly, risking damage. Engineers typically include systems that regulate ascent speed, but these systems must function across a wide range of pressures. Data collected during the mission must remain intact. Storage devices must protect information despite temperature fluctuations and pressure changes. Some systems transmit data to the surface during ascent, but acoustic communication remains slow. Most data transfers occur after the vehicle reaches the ship, but only if the memory system has avoided pressure-related failures. Engineers must design redundancy into storage systems to prevent data loss. Once the vehicle surfaces, recovery involves another set of challenges. Rough seas may make retrieval difficult. The vehicle must remain visible and buoyant until crew members can secure it. If waves push the vehicle into the ship or against other objects, it may sustain damage. Engineers may include flashing beacons or tracking devices to assist recovery teams, but these devices also must withstand deep-sea conditions. After the mission ends, the vehicle undergoes inspection. Engineers check for microfractures in the hull, worn seals, corroded connectors, and damaged sensors. Even a successful dive can leave components weakened. Repairs and replacements may be necessary before the next mission. This maintenance cycle limits how many dives the vehicle can perform within a given time frame. Despite all these challenges, deep-sea vehicles continue to improve through research and development. Engineers study data from past missions to refine designs. They analyze materials for better durability. They optimize battery systems for better energy density. But each advancement introduces new complexities. A more powerful thruster might require a stronger housing. A larger battery might require more buoyancy. Higher resolution cameras need more power and better lighting. Every improvement affects the overall design. Technology meets the abyss not as a flawless system, but as a series of compromises. Engineers cannot eliminate every risk. They must choose which limitations matter most for each mission. Some missions focus on mapping and require long endurance. Others prioritize sampling and need robust robotic arms. Others seek biological observation and require sensitive cameras. The Hadal zone forces engineers to tailor each mission to the environment. As we move into the next section, the focus shifts more directly toward the organisms that share these depths with the machines. Their adaptation strategies differ greatly from the engineered approaches humans create. Understanding those strategies helps reveal how life survives in conditions where technology struggles to function. Life in the Hadal zone reflects a set of conditions that appear harsh by human standards, but function as normal operating environments for the organisms that live there. These creatures do not treat pressure or darkness as threats. Instead, they develop biological structures and internal systems that use those conditions as part of their regular functioning. Every adaptation they evolve solves a problem that machines struggle with. which is why the contrast between engineered solutions and biological ones becomes so clear at these depths. When looking closely at the organisms that inhabit trenches, it becomes easier to understand why life can thrive in places where technology faces constant limitations. Most of the organisms in the Hadal zone occupy niches shaped by limited food supply, low temperatures, and constant pressure. To survive, they rely on slow metabolism, efficient energy use, and structural simplicity. They don't waste energy on unnecessary features. They don't develop organs that don't serve a purpose. Every part of their anatomy contributes to stability and function under the conditions surrounding them. One example of adaptation appears in fish species that inhabit depths beyond 6,000 meters. These fish do not use gas-filled swim bladders to control buoyancy. A swim bladder would collapse instantly under Hadal pressure. Instead, they regulate buoyancy using fats, specialized proteins, and careful control of internal fluids. The distribution of these fluids helps the fish maintain neutral buoyancy without relying on structures that pressure could crush. Their muscles contain compounds that remain flexible at depth, preventing stiffness from cold temperatures and compression. Cellular adaptations become increasingly important as pressure rises. The cells of Hadal organisms contain molecules that stabilize proteins. Under immense pressure, proteins risk unfolding or misfolding, which disrupts their function. Shallow water organisms do not face this problem, so their tissues would fail quickly if exposed to Hadal conditions. But Hadal species produce compounds that ensure proteins retain their structure. These compounds adjust how proteins move and bend, preventing the damage that pressure might cause. Cell membranes also adapt. A membrane must remain flexible enough to allow nutrients, ions, and signals to pass through, while staying stable in the surrounding conditions. Extreme pressure tends to compress membranes, making them rigid. To counter this, Hadal species adjust their lipid composition. They use molecules that maintain membrane fluidity, even when pressure compresses the surrounding water. These chemical changes allow cells to function normally, supporting metabolism, communication, and energy production. Organisms in the Hadal zone vary greatly in appearance. Some species resemble their shallower relatives but differ internally. Others look entirely distinct. For example, amphipods living in trenches have bodies adapted for maneuvering along sediments and capturing small particles. Their exoskeletons contain materials resistant to pressure. Their internal fluids match the surrounding water in density to minimize mechanical stress. These features allow them to move efficiently without struggling against the environment. Many Hadal organisms are small, but certain species grow to larger sizes than expected. Scavenging amphipods in particular can reach sizes greater than similar species found in shallower waters. This relates to the availability of food and the metabolic strategies that maximize energy use. When a large food fall reaches the seafloor, scavengers must consume it efficiently. Larger size can help them dominate feeding sites, especially when competition is low but unpredictability is high. Their bodies handle the pressure without requiring complex skeletal structures because their internal fluids balance with their external environment. Predators in the Hadal zone often develop slow but precise hunting strategies. Because prey is sparse, predators must detect movement efficiently. Many species use long, sensitive appendages that detect vibrations. These appendages pick up small pressure waves created by nearby movement. The vibrations travel long distances in the dense water, allowing predators to locate prey even in complete darkness. Vision becomes secondary or non-existent. The emphasis on vibration detection simplifies biological design while improving hunting efficiency. Some organisms retain limited vision. Their eyes adapt to detect faint bioluminescent signals or slight changes in the environment. These eyes are often large relative to body size, not for precise image formation, but for maximizing the ability to monitor any trace of light. These organisms do not rely on sharp vision but on sensitivity. This sensitivity provides just enough information to navigate or detect nearby organisms without requiring complex visual processing. Bioluminescence occurs in some Hadal species, though not as frequently as in mid-water regions. The bioluminescent signals serve specific purposes. Some organisms produce brief flashes to deter predators. Others emit steady glows used for communication. The biochemical reactions involved depend on compounds stable under high pressure. Organisms must maintain these compounds without allowing them to break down or react unpredictably. Pressure influences how these chemical reactions occur, so Hadal species produce molecules adjusted for those conditions. The structure of organisms in the Hadal zone reflects slow movement and conservation of energy. Many species have elongated bodies designed for gliding or drifting instead of constant swimming. Fins or limbs often appear reduced, streamlined, or adapted for minimal force output. Movement in this environment depends on efficiency, not speed. Any organism that wastes energy will struggle to survive because food is rare and unpredictable. Food sources for Hadal organisms include small particles descending from upper waters, carcasses from larger creatures, microbial mats forming over sediments, and chemical deposits near specific geological features. Organisms develop specialized feeding strategies depending on which foods they target. Some species filter small particles from the water, others sift through sediments, extracting organic matter. Scavengers detect chemical signals from decaying material and gather quickly when a carcass arrives. The arrival of a large food item, such as a dead whale or shark, transforms the area temporarily. Scavengers gather in large numbers. Bacteria break down soft tissues. Crustaceans feed on leftover matter. Over time, only bones remain, and these bones provide nutrients for specialized microbes. This slow decomposition process introduces nutrients into sediments, supporting microbial communities and smaller organisms. Microbial life plays a central role in Hadal ecosystems. Microbes form the foundation of the food web in places where sunlight does not supply energy. These microbes break down organic matter, process chemicals in sediments, and recycle nutrients. Their metabolic pathways operate efficiently under high pressure. Some microbes rely on chemical reactions involving minerals in the sea floor. Others use organic compounds that drift down from shallow waters. Their strategies vary, but their role remains essential. They transform the environment into a place capable of supporting more complex life. Certain trench environments contain small pockets, where chemical conditions differ from surrounding areas. In these pockets, unique microbial communities thrive. These microbes influence the distribution of nutrients and the behavior of larger organisms. Their presence introduces variability into the ecosystem. Some organisms develop symbiotic relationships with microbes, relying on them for nutrition or chemical processing. These relationships support survival in environments lacking predictable resources. Life cycles in the Hadal zone operate at a slower pace than in shallower waters. Growth rates are lower because limited food restricts energy intake. Reproduction often depends on releasing eggs or larvae into the surrounding water. These eggs must survive long enough to encounter mates or drift into environments supportive of development. Parents rarely provide care. Instead, reproduction depends on probability. Organisms maximize reproductive success by producing many offspring or by timing releases with environmental cues. Larvae in the deep ocean often float into higher layers of the water column, where conditions are less extreme. As they grow, they descend gradually toward the Hadal zone. This vertical movement allows them to access different food sources during development. Once they reach adulthood, they settle into the depth permanently. This life cycle distributes populations across different layers of the ocean, increasing the chances of survival. Competition for resources shapes many aspects of behavior. In an environment where food is scarce, organisms must avoid unnecessary conflict. Some species occupy narrow niches to reduce overlap. Slight variations in feeding strategy or movement pattern allow multiple species to coexist. For example, one species may feed primarily on suspended particles, while another focuses on sediment layers. Even small differences in preference reduce direct competition. Adaptations in body chemistry allow organisms to survive despite the cold temperatures. Enzymes must function efficiently at low thermal energy levels. If enzymes slow too much, essential reactions cannot occur. Hadal species evolve enzymes that remain active at near freezing temperatures. These enzymes differ chemically from those found in shallow water organisms. They bend and move more easily. Their structures remain flexible, maintaining reaction rates that support life. Pressure and temperature also influence reproduction timing. Some species reproduce throughout the year, while others use internal cycles. Without sunlight, seasonal cues become irrelevant. Reproductive behavior depends on internal rhythms or subtle environmental changes such as shifts in current patterns or food availability. Movement patterns reflect strategies that reduce energy expenditure. Instead of swimming constantly, many species drift using slow, controlled motions. Their bodies often contain gelatinous materials that increase buoyancy and reduce muscle needs. Gelatinous tissues compress slightly under pressure without losing function. These tissues do not require extensive blood supply or complex structure, making them efficient in an energy-poor environment. Certain organisms exhibit extreme fragility. Their bodies appear delicate when viewed through cameras. These species rely on the stability of the Hadal environment. Pressure, cold temperatures, and darkness remain constant, so they do not need thick protective structures. This fragility makes them vulnerable to changes in pressure or temperature. When brought to the surface, they often disintegrate or lose their shape. This creates difficulties for researchers attempting to study them. Because of these adaptations, Hadal organisms rarely survive outside their native depth. Even slight pressure changes can disrupt internal chemistry. Their bodies depend on equilibrium with their environment. This equilibrium makes them highly specialized but limits their ability to move beyond their niche. Machines entering the Hadal zone temporarily disrupt local conditions, but organisms quickly adjust when the disturbance passes. Predation at depth occurs without the speed or aggression seen in shallow waters. Predators rely on efficiency. They wait motionless for cues. Their attacks are short, decisive, and accurate. Prey respond by minimizing movement, hiding in sediments, or drifting slowly to avoid detection. This dynamic creates a calm but constant balance between predator and prey. The structure of population distribution in trenches varies depending on available resources. Some areas support dense clusters of organisms due to nutrient accumulation. Other areas remain sparsely populated. These distributions shift over time. A foodfall may attract organisms temporarily, but once the food disappears, populations disperse again. Researchers studying population dynamics in trenches must account for these temporary fluctuations. Interactions among species remain complex despite the simplicity of individual adaptations. Microbes process nutrients that support small invertebrates. Invertebrates feed predators. Scavengers recycle organic matter. Each group influences others. The slow pace of life hides the constant exchange of energy and resources. The Hadal zone contains an active ecosystem, even if the activity unfolds slowly. Observing these organisms reveals both the resilience and fragility of deep-sea life. Their adaptations allow them to function under conditions that break most biological systems, but they remain vulnerable to disturbances outside their narrow environmental limits. This combination of strength and limitation explains why studying Hadal organisms requires careful planning. Bringing them to the surface changes their environment too drastically. Researchers must use tools that preserve pressure and temperature to observe them accurately. As we continue, the focus shifts toward the mysteries still hidden in these depths. Despite the presence of specialized organisms and advanced technology, much remains unknown about the trenches. The next section moves into the parts of the Hadal zone that machines cannot yet reach fully, and the unanswered questions that make this environment one of the least understood on the planet. Even with the progress made in deep-sea exploration, the Hadal zone continues to contain large gaps in our understanding. The combination of pressure, darkness, terrain, and the limits of equipment creates areas that remain unseen. Not unseen in the sense that they are hidden behind obstacles, but unseen because reaching them consistently and safely is still beyond current capability. This gap between what we know and what we suspect introduces uncertainty into almost every scientific question about the trenches. For every discovery made by a submersible or autonomous vehicle, there are many regions that no mission has touched. That lack of direct observation shapes how researchers interpret data and design future investigations. One reason the Hadal zone remains mysterious comes from the limited amount of time machines can spend at depth. Even the best deep-sea vehicles operate under strict energy constraints. Batteries must power navigation, thrusters, lights, cameras, sensors, robotic arms, and onboard processors. The deeper the machine goes, the more power it uses. Thrusters work harder in compressed water. Lights must illuminate particles that scatter easily. Sensors must collect data under low visibility. Because of these demands, vehicles often have only a few hours on the seafloor. That is far less time than needed to survey a trench that may extend for hundreds or thousands of kilometers. Another layer of mystery comes from the difficulty of returning to the same location. Without GPS, navigation depends on inertial systems, sonar mapping, and acoustic transponders. These tools work, but shallow errors accumulate. A vehicle might drift a few meters off course without realizing it. Over the length of an entire dive, these small deviations add up. When a machine returns to the surface, reconstructing its exact path requires careful analysis. Even then, uncertainty remains. This makes repeated observations of the same site challenging. Researchers trying to study long-term changes in a specific area often struggle because the environment shifts and the vehicle may not land in precisely the same spot twice. Limited visibility also plays a role. Cameras rely on artificial lights, which illuminate only a small area. Beyond the reach of those lights, darkness remains complete. Even high-sensitivity imaging cannot extend visibility indefinitely. This narrow field of view means that most observations focus on small patches of the seafloor. Many organisms likely remain undetected simply because they live slightly out of frame. A species that stays in a nearby crevice might never appear on camera. A slight change in vehicle angle or lighting might reveal something entirely new, but only by chance. Sonar helps map the larger environment, but sonar resolution decreases with distance. High-resolution sonar systems need to be close to the seafloor to capture detailed features. When mapping wide areas, sonar data may blur together. Small ridges, cracks, or organisms become indistinguishable from background noise. This leaves large gaps in knowledge about the fine structure of trenches. Even features that appear smooth on sonar could be covered in small formations unseen by cameras. Environmental changes further complicate understanding. Trenches are shaped by geological forces that continue to operate. Sediment falls, small landslides, and shifting tectonic boundaries alter the environment over time. These changes might be subtle, but they influence the distribution of organisms, sediment layers, and chemical gradients. Without consistent monitoring, these shifts remain undocumented. Researchers must interpret the landscape based on snapshots taken at different times under different conditions. Another source of mystery comes from the limited number of dives. Conducting a single Hadal dive requires significant resources. Research expeditions take time to organize. Weather delays can interrupt missions. Equipment failures reduce available dive opportunities. As a result, entire trenches remain unvisited. Many of the deepest points documented in maps come from sonar readings collected by ships passing overhead, not from direct observation. These maps reveal the general shape of trenches, but they cannot show details of the seafloor or the organisms that live there. Food availability in trenches contributes to unpredictability. Large food falls happen irregularly. When a whale carcass or other substantial source of organic material sinks to the sea floor, It transforms the local ecosystem temporarily. Scavengers gather, microbial activity increases, and nutrients spread through sediment. If a vehicle happens to be present during such an event, the observations may differ dramatically from those taken during times of scarcity. Without repeated visits, it becomes difficult to distinguish normal conditions from temporary surges. Microbial life contributes another layer of mystery. Microbes occupy every part of the trench environment, including sediment layers, rock surfaces, and water pockets. Many of these microbes operate under conditions that remain difficult to replicate in laboratories. Pressure-retaining systems help preserve samples, but some microbes still fail to survive the journey. This means researchers often rely on indirect measurements, chemical analysis, and genetic sequencing rather than direct observation. Without full understanding of microbial behavior, the roles these organisms play in nutrient cycles remain partly speculative. Chemical gradients also shape the environment in ways that remain incompletely understood. Variations in salinity, dissolved gases, and mineral content occur at fine scales. Some areas experience slight chemical differences due to local geological activity. These differences influence which organisms can survive and how they function. Because deep-sea vehicles cannot sample every region, researchers must infer patterns based on limited data. A region that appears chemically uniform may contain multiple distinct microenvironments that only detailed sampling could reveal. Another complication arises from the behavior of organisms. Some Hadal species remain hidden in sediments. Others drift through the water column and only appear at depth occasionally. Some move through narrow crevices that cameras cannot reach. A few species may spend most of their lives in areas too steep or too unstable for vehicles to approach safely. These organisms remain unknown, not because they are rare, but because they inhabit spaces technology struggles to access. The movement of water adds yet another variable. Deep-sea currents shift sediments, transport organic matter, and influence the distribution of organisms. These currents change slowly over time, and their patterns differ between trenches. In some areas, currents carry nutrients from upper layers. In others, they concentrate particles in specific pockets. The presence or absence of these currents affects local ecosystems. Without detailed measurements across large regions, researchers cannot fully understand how currents shape biological patterns. Geological activity also contributes to uncertainty. Subduction zones, where one tectonic plate moves beneath another, create trenches. These processes continue today. Earthquakes, fault shifts, and volcanic activity alter the environment. Even small geological events may create temperature or chemical anomalies. These events might last hours, days, or longer. Without continuous monitoring, researchers may never detect them. The data that does exist captures only brief periods, leaving many geological processes unexplored. The limitations of technology also affect how researchers interpret data. Instruments provide measurements, but these measurements require context. A temperature reading becomes meaningful only when compared to surrounding data. A chemical reading needs comparison with nearby areas. A biological observation needs knowledge of population distribution. Because data sets remain incomplete, interpretations often include uncertainty. Researchers must identify patterns based on small amounts of information and then test these hypotheses in future missions. Some of the mystery arises from the difficulty of studying life under extreme pressure. Even when samples reach the surface safely, recreating Hadal conditions in laboratories remains challenging. Pressure chambers help, but they cannot perfectly recreate the natural environment. Subtle differences affect experimental results. For example, pressure influences enzyme function, membrane behavior, and chemical reactions. These interactions may differ slightly in artificial systems. Researchers must interpret results cautiously, understanding that laboratory conditions may not fully match natural ones. The structure of trenches varies greatly, and each variation influences what researchers can observe. Some trenches have steep walls that prevent machines from entering certain zones. Others contain complex networks of ridges and basins. Some have large flat floors, while others contain uneven surfaces. The variation affects how organisms distribute themselves and how vehicles move. Each trench becomes a unique environment with its own patterns, challenges, and features. The scale of trenches contributes to the mystery. A trench might be hundreds of kilometers long and several kilometers deep. Surveying even a small portion thoroughly takes time and resources. Even when vehicles cover significant ground, their field of view remains limited. Large expanses remain unexplored simply because missions cannot cover enough area. The problem becomes similar to exploring a vast landscape using only small windows spaced far apart. Another layer of mystery comes from the way trenches isolate biological populations. Many Hadal species may exist only in a single trench or even a single section of a trench. Genetic studies indicate that species separated by relatively small distances may diverge significantly. This suggests that trenches function like islands, with limited connectivity. If a vehicle visits only one trench, it might miss entirely different species living elsewhere. Because each trench may host unique organisms, the full diversity of Hadal life likely exceeds current estimates. Researchers also suspect that certain features, such as deep crevices or small basins, may contain unique ecosystems. These features remain difficult to access due to their narrow openings or unstable walls. A vehicle cannot easily maneuver into these areas, and even if it could, lighting and sonar might not provide clear data. These inaccessible zones may host species adapted specifically to those conditions. Without direct observation, their existence remains hypothetical. Another area of uncertainty involves how nutrient cycles operate at depth. Microbes break down organic material, but the full extent of these processes remains unknown. Chemical compounds in sediments may undergo transformations that only occur under high pressure. These reactions could contribute to global nutrient cycles in ways not yet understood. Without sampling large areas consistently, researchers can only approximate how these cycles function. The presence of Hadal organisms that rise occasionally into higher layers introduces additional questions. These organisms may transport nutrients or genetic material upward. Their movement patterns remain poorly documented. If they ascend only rarely, or only under certain conditions, vehicles may not capture the behavior. This limits understanding of how energy moves between different ocean layers. Some mystery comes from equipment limitations. Even when vehicles record data, sensors may not register everything present. Cameras may miss small or fast-moving organisms. Sonar may overlook features hidden behind others. Chemical sensors measure specific compounds, but may not detect subtle interactions. Each tool offers a partial view. Only by combining multiple instruments can researchers approach a complete picture. But combined instruments require more power, space, and complexity, which limits how many can be included on a single mission. Time also plays a role. The deep sea changes slowly, but it does change. Over years or decades, sediments shift, organisms move, and chemical conditions evolve. Observations taken decades apart may reveal differences, but without continuous monitoring, the causes of those differences remain unclear. The lack of time series data makes it difficult to build models that predict environmental changes. Because of these factors, researchers often approach the Hadal zone with more questions than answers. Every mission uncovers new information, but each discovery highlights how incomplete current knowledge remains. The mysteries are not limited to biology or geology. They include the interactions between organisms, the stability of chemical gradients, the behavior of deep-sea currents, and the distribution of species across trenches. As exploration continues, the unknown parts of the Hadal zone stand as reminders of how much remains unstudied. The combination of environmental challenges and technological limitations explains why the deepest parts of the ocean remain one of the least mapped and least understood environments on Earth. Even with the efforts made so far, technological capability and expedition frequency still limit the scale of what can be observed. As we continue forward, the attention shifts to why these hidden spaces persist, why the deep retains its secrets, and why even advanced machines cannot erase the boundaries imposed by nature. The next section moves deeper into understanding the barriers that keep these mysteries intact and the reasons the environment resists full exploration despite ongoing research. The Hadal zone remains one of the least understood places on Earth, not because researchers lack interest or determination, but because every barrier in the environment works together to limit what can be seen, recorded, or measured. The deep does not actively hide anything, but the conditions function like a natural filter that slows access to information. These conditions restrict how often machines can visit, how long they can stay, how far they can travel, and how thoroughly they can observe. As a result, large parts of the trenches remain unexplored, and each new discovery raises more questions than it answers. Understanding why these secrets persist involves looking at the combination of physical, biological, and logistical factors that reduce the visibility of the Hadal world. One of the most basic reasons the deep protects its secrets comes from simple geography. Trenches form in narrow, isolated regions. Many of them lie far from land, in areas difficult to reach by research ships. Even reaching these locations requires time, fuel, and careful route planning. Weather conditions in open oceans are unpredictable, and storms can delay or cancel missions. For research teams working within limited time windows, these delays reduce the number of dives possible during an expedition. A trench might be visited only once every few years, and some trenches have never been visited at all. The remoteness alone prevents continuous study. Another reason is the scale of the trenches themselves. Even a single trench extends for hundreds of kilometres, with slopes, plateaus, and basins that vary widely in depth and structure. A deep-sea vehicle may explore just a small fraction during a dive. Even multiple dives cannot cover an entire trench. This creates large gaps in understanding. Important features may exist just beyond the range of the vehicle's lights or sonar. Entire communities of organisms might live in pockets that machines never reach. When the explored areas are so limited compared to the total environment, many parts remain unseen. Pressure is another constant barrier. Machines that reach the bottom of a trench endure forces that push materials to their limits. Engineering can compensate for this, but only to a point. Pressure influences every system on a vehicle, from the hull to the sensors. It reduces the reliability of mechanical parts. It increases the chances of fatigue or failure. Because vehicles must return safely, engineers design them with conservative safety margins. These margins reduce how much risk a mission can take. If a trench contains narrow passageways or steep inclines, vehicles cannot approach them without risking damage. This naturally limits where exploration can occur. Temperature adds another constraint. The cold of the deep slows chemical reactions, stiffens materials, and reduces battery efficiency. Batteries last only a few hours under these conditions. Lights must be used sparingly to conserve energy, which limits visibility. Thrusters consume significant power when operating in cold, dense water. If a vehicle uses too much energy early in the dive, it must abandon parts of the mission to ensure it can ascend safely. As a result, many planned observations never happen, and the data collected covers only a short period of time. The absence of natural light means machines must supply their own illumination, but artificial lights change the environment. Light attracts or repels organisms. Some species move away while others draw near. A camera illuminated by bright LEDs may capture organisms that normally stay hidden and miss organisms that avoid artificial light. The presence of the machine itself creates disturbances that alter the surroundings. This means some natural behaviours remain unrecorded simply because the act of observing changes the scene. Sediments create additional challenges. The seafloor in trenches often consists of fine grains that respond immediately to disturbance. When a vehicle lands or uses thrusters to reposition itself, currents stir sediment clouds. These clouds obscure visibility for minutes or even hours. If the mission relies on visual observation, sediment becomes a major obstacle. Even small adjustments in positioning can create large clouds that block cameras. Because sediment settles slowly in still water, vehicles must wait or navigate blindly. This limits how many tasks can be completed in a single dive. Terrain complexity plays a major role in protecting the deep secrets. Trenches contain steep walls, narrow ridges, deep basins, and unpredictable slopes. Some areas are too steep for vehicles to land safely. Others contain unstable sediments that might slide if disturbed. Rocks may fall from heights when vibrations from thrusters shake loose debris. Engineers must avoid these hazards. This means many areas, especially those with complex features, remain unreachable. Even when sonar indicates interesting formations, vehicles cannot approach without taking significant risks. As a result, some of the most geologically interesting structures remain unobserved. Communication limitations add another barrier. Acoustic signals must travel through thousands of meters of water before reaching the surface. These signals distort, scatter, and weaken. Communication delays make real-time control difficult. If a vehicle encounters unexpected conditions, operators may be unable to intervene. Vehicles must operate autonomously, which restricts the complexity of missions. Complicated tasks requiring fine control, such as approaching a narrow opening or collecting delicate samples, become impractical. Without precise control, many areas cannot be explored thoroughly. Biological factors contribute to the mystery as well. Many Hadal species remain hidden within sediments or small crevices. These organisms do not move through open water often. They may appear only under specific conditions. Because machines cannot remain at depth for long periods, they observe only a small slice of biological activity. Seasonal changes, reproductive events, feeding cycles, and other behaviors may go unrecorded. If an organism appears only rarely, or only in specific microhabitats, the chance of detection decreases further. Some organisms behave unpredictably when disturbed. The arrival of a submersible introduces sound, vibration, and light. Sensitive species may retreat, others may freeze, altering their typical movement patterns. This makes it difficult to study natural interactions. When behavior changes in response to observation, researchers cannot build accurate models of ecosystem dynamics. This gap between observed behavior and natural behavior keeps many biological processes unknown. Chemical gradients complicate study even more. Trenches contain variations in mineral content, salinity, dissolved gases, and temperature. These variations occur over small scales and influence microbial communities. Microbes drive chemical cycles in sediments and water. They play crucial roles in nutrient processing, but without detailed sampling across the entire trench, the full picture remains incomplete. Because sampling equipment must operate within pressure-resistant housings, it cannot easily collect multiple small samples across a wide area during a single dive. Time and energy limits restrict how many samples a mission can gather. Another factor that protects the deep secrets is the unpredictability of geological events. Even small earthquakes can reshape parts of a trench. Landslides may bury sections of the seafloor or reopen previously inaccessible areas. Hydrothermal activity may emerge or disappear. These changes occur irregularly and without warning. A single dive cannot capture these shifts. Without constant monitoring, the geological timeline remains fragmented. The environment changes slowly compared to human timescales, but even small shifts influence where organisms live and how resources distribute. The separation between trenches creates another layer of mystery. Each trench functions like an isolated ecosystem. Populations remain separated by geography, pressure extremes, and incompatible environmental conditions. Organisms from one trench seldom migrate to another. This isolation leads to specialization. Species evolve traits unique to local conditions. Without exploring every trench extensively, researchers cannot know how many unique species exist. Many species identified from genetic sequencing may represent organisms never directly observed. Structural features within trenches hide microenvironments that resist exploration. Crevices, overhangs, and small caves create protected spaces. These spaces may contain species adapted to extremely narrow conditions. Cameras and sonar cannot easily detect organisms in these locations. Even vehicles small enough to approach may create disturbances that cause organisms to retreat deeper. Because these microenvironments remain out of reach, they preserve species from observation, delaying their discovery. Technology itself introduces limitations that protect the deep secrets. Every vehicle carries a finite number of sensors. Even advanced machines cannot measure every variable. Some sensors detect temperature but not mineral content. Others detect biological material but not chemical gradients. The gaps between sensor capabilities create gaps in understanding. A vehicle may observe an interesting scene without capturing all the data needed to interpret it fully. When crucial variables go unmeasured, researchers can only speculate about the underlying processes. Funding and logistical constraints contribute to the preservation of mystery. Deep-sea missions cost significant amounts of money. Not every research question receives funding. Even when tools exist, they may remain unused due to cost. Ships with deep-sea capabilities are limited. Expertise is concentrated in a small number of institutions. Because the number of missions is small compared to the size of the Hadal region, exploration remains incomplete. Weather and sea conditions at the surface determine whether a mission can begin, continue, or be completed. Even perfectly planned dives can be cancelled or delayed due to storms. Rough seas make deployment dangerous. High winds or unstable wave patterns increase the risk of equipment loss. Because deep-sea missions require calm conditions for safe, lowering and retrieval of vehicles, weather windows limit opportunities for research. Another barrier comes from the fragility of the environment. If researchers attempt to explore certain areas too aggressively, they risk damaging ecosystems or destroying delicate structures. Ethical considerations require caution. When the environment contains species that cannot survive pressure changes, sampling must be limited. This further reduces what can be observed directly. Researchers must balance curiosity with responsibility, which restricts access to certain types of data. The deep secrets persist partly because of the slow pace of life. Biological processes unfold over long timescales. Growth, decay, reproduction, and nutrient cycles progress slowly. A short-term observation may not capture the processes fully. Without long-term monitoring, researchers cannot identify patterns that take years or decades to form. But long-term monitoring requires instruments capable of staying at depth for extended periods. These instruments must withstand pressure, avoid battery depletion, and survive potential geological disturbances. Designing such long-lasting equipment remains difficult. Communication limits affect long-term monitoring as well. Instruments placed on the seafloor must store data until recovery. Without a reliable way to transmit data to the surface, researchers cannot receive information in real time. If an instrument fails before recovery, data may be lost. This discourages long-term deployments in areas where retrieval may be risky. Without continuous data, many long-term processes remain hidden. Another reason the Hadal zone retains secrets is the unpredictability of rare events. Some biological or geological phenomena occur only occasionally. A large food fall might happen once every few years. A rare species may migrate into a region only under specific conditions. If a vehicle is not present at the right moment, these events go undocumented. Because missions occur infrequently, the likelihood of capturing rare events remains low. The immense pressure protects certain materials and structures by preventing them from being easily disturbed. Fossils or ancient sediments may lie preserved for long periods. But because reaching these layers requires drilling or sediment penetration, researchers cannot access them easily. Pressure makes such operations difficult. Drilling tools must be extremely robust. Sediment cores may collapse during ascent. These limitations reduce access to geological history contained within trench sediments. Another barrier comes from safety concerns. Every mission carries risk. If a vehicle becomes trapped or damaged, recovery may be impossible. Institutions must weigh the value of exploration against the potential loss of expensive equipment. This cautious approach leads to conservative mission plans. Even when interesting features appear, vehicles may avoid approaching them if the risk is too high. This preserves the unknown but protects valuable tools. Despite these barriers, exploration continues to advance. But each advancement reveals new complexity. The deeper researchers go, the more variation they encounter. Every new discovery expands the list of unanswered questions. The Hadal zone protects its secrets not through intentional concealment, but through the sheer difficulty of accessing the environment fully. As we continue forward, the focus shifts toward what these limitations teach about exploration itself and why confronting the boundaries of knowledge helps us understand the importance of the Hadal zone in shaping scientific curiosity. Spending time examining the Hadal zone, whether through scientific research, cautious exploration, or thoughtful reflection, leads to a recurring realization. The deepest parts of the ocean highlight how much of the world remains outside direct human reach. They underline the limits of our tools and the scale of our ignorance. But instead of discouraging curiosity, these limitations reinforce the value of approaching the unknown with consistent effort, patience, and a willingness to revise assumptions. Studying the trenches shows how much remains undiscovered, not just because of environmental barriers, but because certain forms of knowledge require long-term commitment and gradual progress. This perspective becomes clearer when considering what the Hadal zone reveals about the process of discovery itself. One of the first insights that emerges from studying the Hadal zone is that knowledge often depends on incomplete information. Researchers rarely get a complete view of a trench. A dive might capture images of one slope, collect samples from one area, or record chemical readings from one basin. Each piece of data contributes to a larger picture, but the picture remains unfinished. This incomplete nature of deep-sea exploration demonstrates the value of working with partial understanding while planning for future observations. Instead of waiting for perfect data, scientists analyze what is available and build hypotheses that can be tested gradually. This approach applies not only to oceanography, but to any field where direct observation is difficult. Another insight comes from recognizing how certain environments demand specialized approaches. Tools built for shallow water fail in deeper regions. Materials that perform well at the surface behave differently under pressure. Machines that function reliably in laboratories encounter unexpected issues in the field. The Hadal zone shows that methods must adapt to conditions rather than forcing conditions to fit preferred methods. This flexibility helps researchers design equipment suited to the specific challenges of extreme environments. It also encourages the development of new technologies that might later find uses beyond ocean exploration. A related lesson involves the importance of collaboration. No single researcher or institution can explore the Hadal zone alone. Missions require ships, crews, engineers, biologists, geologists, chemists, and data analysts. They require international cooperation because trenches lie in different parts of the world and demand diverse expertise. When multiple groups share findings, the overall understanding grows faster than any isolated effort could achieve. The Hadal zone illustrates how complex problems benefit from multiple perspectives and skill sets. It reinforces that large-scale scientific progress depends on cooperation rather than solitary work. Studying the deep also reveals the value of persistence. Many missions fail. A vehicle might malfunction. A sampling tool might jam. Weather might cancel a dive. Even successful dives may provide less data than expected. Yet researchers continue to plan new missions because each attempt yields something useful. Persistence becomes part of the process. The Hadal zone teaches that progress often comes from repeated efforts, rather than dramatic breakthroughs. Even small gains accumulate over time. This gradual approach applies to many forms of scientific and personal inquiry, demonstrating that consistency can accomplish what speed cannot. Another insight involves the unpredictability of discovery. Researchers may dive with specific goals but find something entirely unexpected. A new species might appear on camera. A geological formation might contradict existing maps. Chemical readings might indicate previously unknown processes. These surprises show that exploration is not always linear. Sometimes the most significant findings occur while investigating unrelated questions. The Hadal zone reminds researchers that discovery often occurs alongside uncertainty, and embracing that uncertainty can lead to valuable insights. The deep also highlights how scale shapes perception. The trenches contain enormous distances, pressures, and time frames. Observing these scales forces researchers to adjust how they think about environments. Processes that appear slow or static from a human perspective may be dynamic when viewed across geological or evolutionary timelines. The Hadal zone demonstrates that understanding an environment requires acknowledging its scale. This perspective encourages patience and prevents premature conclusions based on limited observations. Biological findings in the Hadal zone teach additional lessons. Organisms survive by adapting to specific conditions. They do not waste energy on unnecessary features. Their bodies reflect efficient solutions to consistent challenges. This clarity of adaptation demonstrates how evolution shapes life according to environmental demands. Instead of striving for complexity for its own sake, organisms develop traits that improve survival in the conditions they face. This efficiency helps researchers appreciate the diversity of strategies life uses to function in challenging environments. The presence of unique species in different trenches also emphasizes the importance of isolation in shaping diversity. Each trench becomes a separate environment, where organisms evolve independently. Small differences accumulate over long periods, resulting in distinct populations. This pattern demonstrates how separation fosters variation and how environmental boundaries influence the distribution of species. The Hadal zone offers a clear example of how life evolves uniquely in different conditions, even when the differences between trenches appear subtle. The fragility of Hadal organisms provides another insight. Their bodies function perfectly at depth, but collapse when removed from those conditions. This fragility shows how survival depends on environmental stability. It also illustrates how studying certain species requires careful handling to avoid damaging them. The need for specialized equipment to preserve pressure-sensitive organisms reveals how much work remains before researchers can fully understand deep-sea biology. It also shows that certain forms of knowledge require indirect approaches or new technologies not yet developed. The Hadal zone demonstrates the importance of scale in time as well as space. Processes at depth unfold slowly. Growth rates are low. Reproductive cycles extend over long periods. Chemical reactions proceed gradually. Observing these slow processes requires patience. Researchers may need long-term monitoring equipment or repeated visits over years. The environment shows that not everything can be understood quickly. Some systems reveal their patterns only when studied over long timescales. This encourages a broader view of research that considers decades rather than days. Another insight involves the limitations of human perception. Humans rely heavily on vision, but vision becomes irrelevant in total darkness. Machines use lights, but lights illuminate only narrow areas. Sonar and other sensors capture different kinds of data, but each has limits. Studying the deep requires tools that extend perception beyond normal senses. This reliance on instruments highlights the constraints of human perspective and the need for technological extensions. It also shows how environments unfamiliar to human experience require new ways of interpreting information. The deep reveals the importance of designing systems that account for failure. Even well-tested equipment may malfunction. Pressure may cause unexpected mechanical issues. Sediment may clog thrusters. A battery may drain faster than anticipated. Engineers must anticipate these possibilities. They design redundancy into systems, allowing vehicles to recover from partial failures. This emphasis on resilience demonstrates how planning for failure increases the chances of success in complex environments. The Hadal zone also teaches that not all mysteries require immediate answers. Some questions remain open because solving them requires tools or techniques that do not yet exist. Instead of treating these gaps as failures, researchers view them as opportunities for future investigation. The presence of unsolved questions motivates technological development. It encourages exploration and innovation. The deep shows that mystery can inspire progress rather than hinder it. Another lesson comes from the way trenches preserve certain forms of knowledge. Sediment layers capture history. Chemical deposits reveal past conditions. Patterns in species distribution hint at ecological changes. These preserved records demonstrate how environments store information over long periods. But accessing this information remains difficult. Understanding it requires careful sampling, analysis, and interpretation. The deep shows that knowledge often exists but remains hidden until methods improve. The Hadal zone also highlights the importance of boundaries. Pressure, darkness, temperature, and terrain create natural limits. Instead of crossing those boundaries easily, researchers must work within them. These limits teach respect for physical constraints. They show that certain environments cannot be approached in the same way as others. They encourage creative problem solving and remind explorers that nature's rules remain non-negotiable. Another insight concerns the relationship between observation and disturbance. Even the act of exploring changes the environment slightly. Lights attract or repel organisms. Thrusters stir sediments. Cameras alter behavior. Recognizing this influence helps researchers interpret data more accurately. It reminds them that observation is not passive. The deep teaches that studying an environment requires awareness of how tools affect that environment. Studying the trenches reveals the value of incremental progress. Each dive builds on the previous one. Each sample refines understanding. Each measurement adds context. This gradual accumulation of knowledge demonstrates how large scientific questions can be approached through small steps. The Hadal zone teaches that progress does not always require large leaps. Consistent effort yields results over time. The trenches also highlight the connection between technology and knowledge. As tools improve, observations improve. New materials allow deeper dives. New sensors capture more precise data. New models interpret information more accurately. The relationship between equipment and understanding becomes clear. Without advancements in technology, knowledge would remain limited. The deep shows how technological development and scientific discovery depend on each other. Another insight involves humility. The Hadal zone contains environments that humans cannot enter without machines. It holds species that cannot survive outside narrow conditions. It operates on scales far beyond daily experience. Confronting this complexity requires acknowledging how little is known. Instead of resisting this uncertainty, researchers learn to accept it and work within it. This humility does not diminish curiosity. It strengthens it by encouraging careful observation and flexible interpretation. The deep also demonstrates the value of patience in scientific inquiry. Because missions occur infrequently and data sets remain small, conclusions emerge slowly. Researchers may spend years studying one region or one species. They understand that answers take time. This patience becomes a core part of the process. Finally, the Hadal zone teaches that curiosity itself remains one of the most powerful tools available. Despite all the challenges, researchers continue exploring because each discovery provides new insight into how the world functions. The trenches highlight the value of seeking knowledge even when the path remains slow or difficult. They show that understanding the unknown depends not only on equipment, but on the willingness to look deeper, ask questions, and return to challenging environments repeatedly. With these observations, the exploration of the Hadal zone continues not as a completed effort, but as an ongoing process shaped by curiosity, careful planning, technological development, and the recognition that unknown regions still contain more to learn than can be seen in any single mission.